A sky of prismatic storms and singing dead suns waits beyond our mapped night. This is a tour of 35 mysterious star systems beyond imagination that rewrite what possible means. Stay until the end, and you will be able to name the 3 systems most worth colonizing and explain the technologies and lifestyles you would need to survive there. I will guide you, space-curious friends, through one system at a time with a vivid description, the science that makes it real or plausible, lifestyle implications for future settlers, and suggested visuals that creators can turn into striking scenes. Expect shimmering glass orchards, twin stars that paint the skies with constant auroras, cold, dark suns that whisper in radio, and a final system so strange it seems to bend the rules of physics. Along the way, we will touch on surprising facts, ongoing controversies, and small ethical puzzles about exploration and preservation. Which of these worlds would you move to if you could? Some skies would look like living stained glass. In the glass orchid system, a single planet wears its atmosphere like sculpture with layers of crystalline haze that bend and split starlight into long-lasting opalescent blooms. Tiny glass-like particles float in bands and petals high above the surface. When starlight enters those layers, it is refracted and scattered, and the colors separate and mingle in slow motion. Some wavelengths are sent one way while others are reflected back and forth between thin layers. That dance of refraction and interference paints the sky in shifting opal and pearl tones so the clouds can look like orchids frozen in color. How could a place like this form? One route starts with a raw abundance of silicon in the local disk. If the protoplanetary cloud cooled unusually slowly, the heavier silicate compounds could condense into microscopic glassy droplets that remain suspended instead of raining out. Another plausible path is driven by chemistry in the upper atmosphere, where energetic light and charged particles build complex silicon-rich molecules that aggregate into tiny spheres of silica. Those spheres act like tiny prisms. Either way, the result is a stratified aerosol layer that refracts light rather than simply hiding it. The planet would most likely orbit a cool orange star at about 9/10 of an astronomical unit, which gives it a long, gentle day and a light spectrum rich enough to feed those opalescent displays. Life on such a world learns to live with constant wonders and unexpected challenges. Habitats would favor adaptive glazing and shaded terraces so people can choose between pure color and filtered comfort. Architects would harvest the spectacle rather than block it using glass facades that channel specific bands of light into energy collectors. Solar systems here would not simply track the sun, they would be tuned to catch the prismatic bouquet of wavelengths spilling from the sky. Multi-layered photovoltaic panels could be designed like a field of petals to capture reds and blues separately and squeeze extra efficiency from the dispersed light. Cultural life would skew toward crafts that play with color. Festivals would celebrate the daily shifts of the orchids, and painters would chase ephemeral palettes in glass studios bathed in refracted light. There is also a tourism economy written in the very air. Balloon ascents into the petal bands could let visitors drift through slow-motion rainbows. High plateau lodges would offer rooms with facades engineered to cast giant prismatic shadows across lawns and pools. Scientists would sell night tours to hear the faint radio signatures of crystal collisions, and artists would choreograph performances that rely on permanent auroras as a living stage light. Visuals for a creator are naturally cinematic. A slow-motion simulation of light splitting through layered cloud petals gives viewers time to feel the shimmer. An artist concept of a city on a plaza that throws prismatic shadows across glass gardens ties human presence to the phenomenon. Close-ups of sculpted cloud formations that sway like orchid petals help the audience connect pattern to scale and texture. Would living under a permanent aurora of color make you happier or dizzy? Two suns locked in a furious orbit light the sky without end. What that looks like is not merely brighter days and double sunsets. The twin stars tug on each other so strongly that their insides twist and churn. That twisting feeds their magnetic dynamos, the invisible engines inside stars that make magnetic fields. When those dynamos run wild, the surrounding space fills with intense magnetic fields and streams of charged particles blasting outward like a constant solar storm. Planets caught in that storm do not see occasional curtains of light near their poles. They wear auroras like a second sky that sweeps across horizons at all hours and in many colors. On Earth, auroras happen when the solar wind pushes charged particles along magnetic field lines into the upper atmosphere where they strike atoms and light them up. On Jupiter, the scale is larger and the mechanism is amplified by a giant magnetic field and by volcanic material from its moon that feeds a dense plasma torus. In an eternal aurora binary, you get both the steady blast of particles and the twisted, overlapping magnetic fields from two nearby stars. Those twisted fields force currents across whole planetary magnetospheres and inject energy into the atmosphere over vast regions. The result is auroras that can glow in the middle of the day, that paint the sky with bands and spirals, and that shift color as different atoms and molecules are excited by different energies. Oxygen can make green ribbons, high-altitude oxygen can make deep red bands, and nitrogen interactions can throw purple and blue into the mix. With two suns, the particle streams can come from different directions and with different energies, so the auroral choreography becomes complex and constant. Living there alters how technology and culture evolve. Electronics must be hardened against electromagnetic surges caused by sudden particle injections. Power grids and transit systems need grounding and isolation to avoid currents induced by shifting magnetic fields. Habitats will favor subsurface or heavily shielded structures using water, regolith, or layers of conductive materials to absorb charged particles. Some cities could deploy active magnetic shields, rings of superconducting coils that distort the local field and steer storms away from vital zones. Those same coils could be used for transit and trade. Magnetic sails operate like ocean sails but against plasma flows. A ship with a large magnetic bubble can catch a stream of charged particles and ride it, trading the plasma flow for momentum and reducing the need for onboard fuel. In such a system, shipping lanes follow plasma highways and pilots learn to tack against currents of charged particles. Daily life would mix ritual and caution. People would plan festivals around the most dramatic storms. Open-air theaters with deployable shields would let audiences watch curtains of light ripple overhead while being protected from particle flux. Musicians and visual artists would use the auroras as raw material, composing pieces that sync with predictable magnetic tides. At the same time, parents would teach children how to read magnetograms like weather maps, and emergency drills for radiation spikes would be as routine as fire drills. Settlements might cling to magnetic quiet zones carved out by engineered fields, while explorers seek raw spectacle in unshielded highlands at the risk of costly exposure. For a creator, the contrast is cinematic. A magnetohydrodynamic simulation can show braided magnetic field lines and the violent exchange between stellar winds. A split-screen sequence could show a coastal city before shielding, with power lines sparking and auroras washing structures. Then the same skyline after shield activation, calm and glowing within a protective halo. Time-lapse footage that compresses weeks of auroral activity into seconds would make the rhythms of that sky feel like music. Close-ups of people listening to plasma radio sounds and weaving light into fabric would give the phenomenon human scale. And yet there is a sharp question at the heart of such a world. Does endless celestial theater make a paradise people will risk and adore? Or does the constant bombardment of charged particles and magnetic volatility create a hazard that forces colonies underground and keeps the most interesting places off limits? Which side of that argument would you choose if the choice meant the difference between standing in the open beneath living light or living behind layers of shielding forever? Some stars whisper instead of shout. In the dark star of Echoes, the primary is a sub-brown dwarf that glows in faint infrared and warms its planets like a distant ember. It is too small for steady hydrogen fusion and too large to be a mere gas giant, so its light is a slow, deep hum of heat left over from its birth and occasional internal reactions. That low energy spectrum shifts the habitable thresholds inward and forces climates to a colder palette, where twilight lasts for ages and surface liquids exist at the edge of freezing or under insulating ice. Planets here tend to conserve heat, developing thick insulating atmospheres or subsurface oceans kept liquid by geothermal flows and tidal flexing, and biochemistry adapts to the chill with slow metabolisms, antifreeze proteins, and membranes made from flexible lipids that stay fluid at low temperatures. Some worlds pool reflective mineral seas made of conductive salts and layered crystals that act like vast mirror lakes for radio frequencies. When radio waves strike those seas, they bounce and scatter and return in long, lingering echoes that can be heard across tens and hundreds of planetary rotations as radio reverberations. Atmospheric layering can trap those waves between a mineral surface and an ionized shell, producing resonant zones where particular bands swell into sustained notes while others cancel into quiet shadows. That strange acoustic of the electromagnetic spectrum reshapes communication and secrecy. Signals sent from one colony may smear into a chorus of delayed copies, confusing simple tracking and making eavesdropping both easier and harder depending on the band, while clever engineers learn to time bursts with echo delays to punch messages through like keyed taps on a giant bell. Entire neighborhoods might shelter in radio-quiet pockets where interference cancels transmitters and leaves spaces invisible to long-range scans, a natural cloak for clandestine habitats and private cultures. Settlements favor low-energy heating solutions, harvesting residual heat with thermally linked stone, heat pipes that move warmth with near no power, and radiant panels tuned to the deep infrared so interiors glow in slow red light rather than bright white. Scenes to show this feel intimate and strange, like infrared telescope mock-ups that reveal the faint primary as a warm smudge, sonar-like animations that paint radio echoes as rippling rings, and interior shots of communal rooms lit by gentle thermal panels where people move with deliberate slowness. In such a place, music might not be percussion and melody as we know it, but long radio notes braided with planetary echoes, and art might be made by carving silence into frequencies rather than by paint on canvas. Would a civilization born to listen to the hum of its star-write symphonies out of echo patterns and build galleries that display living radio sculptures? Beyond echoing planets lies a shape that makes suns feel small. A ring the width of continents wraps a star like a living belt, its inner rim a strip of coastlines, deserts, forests, and engineered towers where wind moves like a secret language. Up close the sound is uncanny, a chorus of air flowing over tuned architecture that turns pressure into long, low notes, a whispering that carries for hundreds or even thousands of kilometers along the rim. From a distance, the band looks like a luminous horizon folded into itself, a continuous city that never ends. How could such a thing come to be? One idea is slow and brutal. A world torn apart by tides or collision leaves debris in orbit. Over long ages, that rubble spreads and grinds, shepherded by gravity into a thin ribbon. Left to settle, fragments accrete, boulders lock together, and a debris ring becomes a continuous surface. That path explains a ring that feels natural, full of irregularities and legacy scars from its violent birth. The other idea is deliberate and dizzying. An intelligence with long reach harvests asteroids and minor planets, assembling segments, splicing materials, and shaping a ring by design. That version is geometry and policy as much as engineering, with outer scaffolds, active station keeping, and intentional climate control. Either way, the scale is staggering. Think of the ring habitats from classic science fiction, with circumferences thousands of times larger than Earth, and inner surfaces whose area could hold whole continents and millions of cities. Walking across one latitude could mean months of travel, and crossing from one cultural belt to another might require crossing climate zones as distinct as different planets. Life on the inner rim is carved into microclimate zones. Small adjustments of tilt and shading produce neighborhoods that mimic temperate valleys, tropical belts, or endless twilight. Towers rise like organ pipes to catch steady rim winds, converting them into power and song. Those same towers shape local weather, channeling breezes into irrigation fogs or into clear corridors for transit. Long-distance trade becomes an art of timing and endurance. Convoys glide along magnetic levitation lines that hug the inner edge, while cargo sails and plasma tugs ferry bulk goods across the shadowed outer face. Trade routes thread through controlled wind corridors, where sound and signal carry differently because the ring itself acts as an acoustic and electromagnetic instrument. Micro-societies nest along latitudes and develop distinct identities. A market city on a warm equatorial belt might glow with open plazas and constant exchange. A high-latitude community in thin sunlight might cultivate slow crafts, glass-blowing from condensed orbital silicate, and festivals that honor patience and silence. Some societies worship the ring as a sacred whole, insisting that maintenance and the rituals of repair are communal duties. Others stake claims, arguing that a latitude of abundant light or rare minerals is theirs by labor or by law. Those claims are where politics and ethics become unavoidable. Who determines access to a sun-drenched belt or to the quiet gardens where wind song preserves ancient memory? Is the ring a shared commons to steward or a resource to parcel and sell? If the structure is built, do the builders retain rights or responsibilities across millennia? If it formed naturally, does transforming it for human use count as harm? Visual storytelling plays this up with obvious spectacle. Start a fly through at a rimmed city, drifting slowly past balconies and wind towers, feeling the whisper swell as you approach a plaza that opens onto the inner expanse. Pull back to a panoramic shot that curves the horizon into a ribbon, and then overlay a comparative scale that places a familiar planet beside the ring, so viewers feel how small a world can be next to such infrastructure. Cut to close-ups of tower flutes emitting visible streams of dust and sound, and to trade caravans threading under aerial bridges that span forever. End with human faces, a negotiator arguing latitude writes in a council chamber, a child listening to the ring sing through a window. Who gets which latitude, who pays for upkeep, and who protects the ring from rapacious harvesters are not only technical problems but moral ones. Which side of that argument would you join when the choice is the difference between claiming a sunlit coast and preserving a chorus that has sung for ages? Light can fall like a wave. A planet in the mirror tide system is covered in seas that are 1 kilometer deep and mirror-like in their smoothness and reflectivity. These are not ordinary oceans of water. They are pools of liquid methane and ethane on worlds that orbit cool orange or red dwarf stars at distances where temperatures sit near the freezing points of those hydrocarbons. Under those conditions, methane behaves like water does on Earth and can gather into vast continuous surfaces that reflect the incoming light with deadly brightness at certain angles. In other variants, the liquids carry suspended metallic or crystalline particles that form a near-continuous skin at the surface. Those skins act like a glass mirror across wavelengths matched to the star. The chemistry is simple and strange. Cooler stars emit more of their light in the infrared and near-infrared. Methane and ethane absorb some bands and reflect others. If the surface chemistry favors a thin film of solidified hydrocarbons or suspended silvery particles, the result is an almost perfect reflector for a wide swath of the star's output. Reflectivity or albedo then feeds back into climate. A highly reflective sea throws a large fraction of incoming light back into space and cools the local atmosphere. Cooler air holds less vapor and reduces cloud formation above the sea, which in turn can increase or decrease reflectivity depending on the balance. That feedback loop can lock regions into stable mirror-dominated climates or flip them into darker states after changes in orbital tilt or volcanic eruptions alter the surface chemistry. The tides themselves are a spectacle. Tidal forces from a close moon or a resonant neighbor can raise kilometer-scale bulges and then sweep vast sheets of mirror across the horizon like a slow-moving glacier of light. At certain angles, sunrise and sunset become blinding. A single blade of bright reflected light can wash an entire bay in white and then, as the mirror folds, leave it in sudden shadow. Survival on such a world requires both awe and caution. Travelers cross the seas in mirror sailboats. These craft do not look like wooden hulls with fabric sails, but like suspended skiffs with broad reflective surfaces designed to catch both wind and photon pressure. The mirror sails can be angled to use reflected starlight to nudge a course and to dump heat when decks overheat under a glare. Pilots learn to tack against light as well as wind and to read the skin of the sea like a weather chart. Settlements hug coastlines, but they do not face the sea like coastal towns on Earth. Architecture here is glare adaptive with layered facades that change polarization and reflectivity on demand. Buildings wear smart skins that roll closed like lids when a bright mirror tide sweeps in and that open as the angle softens. Windows are made from electrochromic glass and photonic lattices that filter the specific reflected bands of the host stars so interiors keep steady lighting without sacrificing the view. Streets and public spaces are recessed under cantilevered shades and plazas are laid out so that glare never aligns with pedestrian paths. For energy systems, the abundance of reflected light becomes an opportunity as well as a hazard. Solar harvesters are tuned not only to direct starlight but also to the reflected spectrum that bathes the world. Arrays use layered photovoltaic materials that separate and capture different bands much like a prism-based plant would. Some fields are mounted on adjustable rigs that track the grazing reflections sweeping across the sea and harvest pulses of concentrated flux. Engineers also design collectors that exploit the temperature contrast between bright reflections and shaded water. Thermoelectric harvesters sit on floating platforms and convert the sudden thermal gradients into steady power. Visuals for a creator are immediate and cinematic. Begin with a point of view on the rim of one of those mirror seas at sunrise when the first strip of reflected light races toward the camera and blinds for a heartbeat. Follow with a slow aerial sweep that shows tides shimmering like walls of glass and boats trimming their broad sails to a ghostly shimmer. Insert a schematic visualization of albedo feedback loops where bright sea lowers air temperature and alters cloud cover, and then show a time lapse of a coast shifting from mirror bright to muted matte after a chemical bloom. Close-ups of adaptive eyewear prototypes help the audience feel practical solutions. Show lenses that polarize and tint within a second and hoods that deploy from collars to shield faces from sudden glare. Finally, consider a thought that turns spectacle into strategy. A civilization could learn to choreograph its mirror seas by coordinating the opening and closing of reflective films across thousands of kilometers, or by guiding tides with floating barriers. A civilization might create patterned flashes aimed at the sky. Those coordinated glints would be like a giant heliograph sending pulses of concentrated light into space. Could mirrored seas be used as interstellar beacons? Could someone watching from light years away notice a planet that blinks with artificial timing and interpret it as a signal? The idea is at once simple and sublime, and it turns the very hazard of blinding light into a possible language across the dark. Some systems are frozen in the act of becoming. A compact nursery can hold dozens of protoplanetary bodies, each locked into a precise orbital dance like gears in a clockwork, and watching one feels like watching planet formation in fast forward. Those young systems are often only 1 to 5 million years old. a brief moment in cosmic terms when dust still swirls thick and embryos of rock and ice are still growing by grabbing pebbles and gas from their surroundings. In that crowded, orderly chaos, gravity writes the rules of motion and resonance is the grammar. Resonance happens when two orbiting bodies settle into a simple ratio of periods, 2:1 or 3:2 for example, so that they tug on each other at the same points in their orbits. Those repeated nudges can stabilize orbits, locking neighbors into steady patterns, or they can amplify motions and scatter material outward. Resonances also carve the disk into lanes. As a forming planet pulls on the dusty gas, it launches waves through the disk that pile up material in some regions and clear gaps in others, leaving visible grooves that telescopes can spot. Those gaps are not just empty spaces, they mark where mass concentrates and where future cores will grow faster, and they are signatures scientists use to read the timeline of formation. The timescale is urgent and delicate. Solid cores can build in hundreds of thousands of years by efficient accretion of small solids, and a runaway phase of gas capture can swell a core into a giant planet within another few 100,000 to 1,000,000 years before the gas disk dissipates. Lose that window and a would-be gas giant becomes a frozen rock. That makes clockwork nurseries priceless natural laboratories. They let researchers test theories about how planets gain mass and migrate, about whether migration leaves scars that explain the odd orbits we see in mature systems, and about how chemistry evolves as solids lock into cores and volatiles are sequestered. Observing embryos at different stages in the same system removes the frustrating variable of differing stellar histories and gives a clearer sequence of cause and effect. The practical lure is strong as well. These young disks brim with volatiles and loosely bound ices that could be far easier to extract than the hard-bound resources of older worlds. A canister of water or organics harvested from a nascent ring might require a fraction of the energy it takes to mine a solid planet. That potential gives rise to an ethical puzzle. If a future civilization can harvest the riches of a nursery, should it? Intervening could speed up or alter planetary growth, rob future worlds of material they need to finish forming, or prevent unique chemical pathways from ever happening. On the other hand, leaving a system untouched may mean turning down resources that could feed billions or enable exploration. The debate echoes a familiar tension between scientific patience and immediate utility. For the people who would live and work there, the lifestyle would be unlike classic colony life. Picture rotating research habitats that never settle. These are compact centrifuge rings and modular hulls that hop between embryos, riding gentle transfer windows from one forming object to the next. Scientists would conduct targeted sampling missions that last weeks to months, then move on to the next site to watch a later stage of accretion. Habitats would be built to be mobile and resilient, with angled shields to face constant dust streams and dynamic thrusters to dodge sudden clumps of debris. Safety protocols would read like seafaring rules, with watch teams scanning for kilometer-scale boulders and instruments tuned to detect changes in local gas density that presage a burst of accretion. The aesthetics of living there borrow from both clean laboratories and ramshackle shipyards. Work corridors would be lined with monitors showing real-time resonance maps and gap evolution, and common rooms would look out through filtered ports at silhouettes of growing worlds lit by the warm glow of the protoplanetary disk. For a creator, the visuals are an embarrassment of riches. Time-lapse accretion disk animations can compress hundreds of thousands of years into seconds to show spiral waves and clearing gaps. Labeled resonance maps can overlay simple ratios on orbits so viewers can feel the geometry that governs motion. Close artist impressions of newborn planets, half cloaked in dust and gas, give human faces something to touch and respond to. Cutaways of a hopping research habitat approaching an embryo convey both intimacy and scale as tiny hatches swing open and drilling rigs extend into soft regolith. The moral scenes are almost cinematic. A team debates whether to extract a cache of pristine ices, while another scientist pleads to delay intervention so the formation can continue. A child on board a habitat watches a simulation of a future planet that might never be if harvest begins now. The nursery forces a question that has followed explorers since the first camps on new shores. Do you become part of the process you study, shaping the outcome, or do you learn to be an ethical witness and risk leaving resources unused? Which choice would you make when a single shipment could feed millions but might also rewrite the future of an entire world? Some stars beat like drums. In the singing pulsar pair, a rapidly spinning neutron star and a wildly magnetic magnetar circle each other close enough that their emissions lock into a haunting rhythm that can be heard across light years when translated into radio sound. The first partner is a pulsar whose rotation can range from a few thousandths of a second to several seconds. Its magnetic field funnels charged particles into narrow beams that sweep past like a lighthouse and create sharp, clock-like radio pulses. The second partner is a magnetar with a field strength so extreme that its magnetic pressure twists and snaps the surrounding space, unleashing bursts that are both powerful and irregular. Pulsar magnetic fields commonly sit in a range from about 100 million to 1 trillion Gauss, while magnetars reach strengths on the order of 100 trillion to 1 quadrillion Gauss. Those are numbers so large they are almost beyond intuition, but their effects are clear and immediate. The physics behind the music is simple in concept and ferocious in practice. Charged particles locked to curved magnetic field lines are forced to accelerate and emit beams of radiation. When one star emits a steady beat and the other adds thunderous, irregular hits, the surrounding plasma does something like a drum skin being struck with varying force. Clouds of ionized gas respond by lighting up in radio bands and by emitting coherent bursts as densities and field geometries change. In some regions, plasma instabilities amplify certain frequencies, producing narrow, pure notes that stand out like overtones. Where the two magnetospheres meet, the interaction can set up standing waves in the plasma so that pulses arrive as layered patterns, a metered beat undercut by unpredictable claps. That patterning is not merely aesthetic. Pulsars are among the most reliable clocks in the universe. Their steady timing has already been used on Earth as a navigation reference in thought experiments and in practice for spacecraft testing. In a system where pulses are both regular and richly textured, you could encode information in the timing and amplitude of subpulses, using slight shifts as a data channel. A colony might lock its timekeeping and communications to a pulsar metronome, letting outposts synchronize with near-atomic certainty across extreme distances. Engineers might modulate pulse trains to carry messages in a form of interstellar Morse, or use predictable beats to schedule automated resource transfers and shield cycling with exquisite precision. Those same properties that enable communication also create profound hazards. Magnetar outbursts produce bursts of X-ray and gamma radiation, intense particle winds, and sudden changes in local electromagnetic fields. Long conductive structures would develop induced currents during strong pulses, frying unshielded electronics and lighting power lines like cosmic fuses. Biological systems face radiation damage and acute particle events that can strip atmospheres from vulnerable worlds if they happen close enough. Preventing harm requires layered defenses. Habitats must be buried under substantial mass, using rock and regolith to absorb high-energy photons. Critical systems need magnetic shielding and current suppressors built from superconducting coils that route charged flows safely away. Electronics must be hardened and made redundant so that a single flare cannot cascade into systemic failure. Timing is safety as well as opportunity. If pulses are predictable, activities with high exposure risk can be scheduled in quiet windows, and systems can spin down or island when a dangerous flare approaches. Beyond practicalities, the singing pulsar pair invites cultural response. Any life that experiences a regular cosmic drum will weave it into stories, The beat becomes a calendar, a ritual cue, the heartbeat beneath poetry. Societies might treat the pulse as sacred and align ceremonies to its accented measures. Artists would sample actual radio waveforms converted to audio and compose pieces that mirror the interstellar rhythm. Children could learn to recite history in pulse counts, and elders might read omens in subtle deviations. Other groups would view the pair with deep wariness and build entire philosophies around avoidance and shelter. Those clashing worldviews produce rich social textures where science, faith, and survival trade places and tangle. For filmmakers and visual creators, the singing pulsar pair is a gift. Radio data can be translated into audible sound so viewers can literally hear the star song. Waveform visualizations that flow into spectrograms help make abstract timing patterns tangible. Animations of magnetosphere field lines can show how the two stars tug and braid each other's fields, and how those changes ripple into surrounding plasma clouds. A dramatic sequence might sync a played audio track derived from real pulsar data with visuals of clouds flaring and dimming, cutting to a settlement where clocks tick in lockstep with the distant drum. Close-ups on instruments clicking and on people pausing to feel the beat would tie cosmic scale to human scale, and there is a debate that sits in the rhythm itself. Do you accept the pulsar song as a natural metronome to structure time and technology, or do you treat it as a siren whose mood can turn deadly without warning and therefore must be treated with utmost distance and fear? Do you dance to the cosmic drum and risk a flare, or do you live off beat and sleep in deeper silence? Which answer would you choose when the music is both a promise and a threat? A clock that keeps you coordinated and a percussion that could, in a single hit, rearrange everything you built. Some nights glow like living emeralds. A cluster of worlds sits under a star that pours out fierce ultraviolet light, and that light teases chemistry into color. These planets carry atmospheres rich in methane and layers of complex organic aerosols, tiny particles born when simple gases break apart and recombine under ultraviolet fire. The thin airborne soot that forms is full of molecules called tholins and long-chained ringed hydrocarbons, flat carbon molecules that soak up high-energy light and re-emit it as visible fluorescence. Under the stronger ultraviolet, this chemistry runs faster and brighter than on places like Titan, and the result is a mist that catches the starlight and returns it as a soft, constant green glow across entire continents. The fog does not simply reflect light. It becomes the lamp itself, a living photochemical veil that pulses faintly with shifting intensity as solar storms and local weather change the chemical mix. Living beneath that canopy rewrites daily life. Cities learn to treat the atmosphere as both spectacle and hazard. Public spaces become intentionally translucent, built from panels and lattices that channel the green shimmer into plazas and galleries, while residential districts favor layered facades and sealed corridors that let people choose how much glow they want in their homes. Air handling becomes a core craft. Habitats use multi-stage filtration that begins with coarse sieves to catch bulk particles, moves to electrostatic precipitators that pull charged aerosols out of the air, and finishes with carbon beds and catalytic scrubbers that break down lingering organic compounds. Ultraviolet photoreactors can be tuned to split stubborn molecules into harmless gases, and living filters populated with engineered microbes trap and metabolize exotic organics into safe compounds or even into feedstock for farms. Portable personal filters and mask systems are common, as are pressurized commuter tubes that ferry people between tightly sealed districts. Health effects push both medical innovation and cultural adaptation. Short-term exposure causes eye strain and irritated airways, and long-term contact with fine organic aerosols seems to correlate with chronic respiratory conditions and changes in sleep patterns. To cope, doctors develop targeted therapies and preventative regimens, and urban planners fold wellness into architecture with quiet green light clinics and filtered breathing parks where children can play in clean air domes. Psychologically, the constant emerald twilight shapes more than biology. For some communities, the green fog becomes central to identity and aesthetics. Neon green pigments and photoreactive fabrics leap from streetwear into civic banners, and artists choreograph light sculptures that feed the fog and coax it into patterns. For others, the perpetual glow feels claustrophobic, and those cultures cultivate indoor palettes that mimic a sunlit spectrum to keep circadian rhythms steady. Markets sell glasses that tune the hue of the fog, and entire neighborhoods compete on their mastery of glare and shade. The environmental engineering is as poetic as it is practical. Designers build glass canopies that act like bell jars for controlled microclimates, and greenhouses use filtered fog as fertilizing mist, turning a hazard into a resource. Ships crossing open plains carry dynamic intake arrays that harvest organics from passing air mats and convert them into fertilizer on the fly. For a creator, the imagery is irresistible. Animation of microscopic aerosols fluorescing under an ultraviolet beam makes the chemistry feel intimate and alive. Cross-section visuals that expose a building S-filtration spine, from intake vents to catalytic cores and living biofilters, translate complex systems into readable human scale. Street-level scenes where vendors sell glowing fruits beneath a gentle haze show how everyday life and wonder can overlap. Close-ups of photoreactive murals changing color as the fog thickens tie culture directly to atmosphere. And there is a law that goes beyond aesthetics. If chemistry paints the nights, could biology learn to sing along? Native organisms might evolve pigments and proteins tuned to the same wavelengths, living lanterns that amplify or modulate the fog's light. Bioprospecting missions would hunt for those creatures, not merely for spectacle but for molecules that could revolutionize medicine, new bio-inspired light sources, or living materials that harvest ultraviolet for power. What would you hope they find when the first probe opens a sample vial and the green glow inside truly begins to pulse with life? A star that seems hollow refuses to be ignored. Telescopes pick up odd beats and strange gaps in the light that do not match any ordinary stellar song. Heliosismology, the study of a star's vibrations like earthquakes, shows modes that ring in patterns scientists did not expect. Spectra reveal missing bands where atoms should absorb light in predictable ways, and neutrino detectors register counts that drift from model predictions in subtle but persistent ways. Those three clues together make the system feel like a riddle written in physics, a puzzle that asks whether something in the interior behaves like a cavity or a region of unexpected density. Before conspiracies take flight, there are careful, mundane possibilities to consider. Stars can host complex magneto-acoustic waves, hybrid oscillations that mix sound waves and magnetic field motion, and those waves can produce unusual heliosismic signatures that mimic the effect of empty regions. Strong internal magnetic fields can trap modes and create spectral oddities by shifting local temperatures and pressures. Sharp composition boundaries created by early migration of heavy elements can make absorption lines look wrong because the expected atoms are sequestered in layers. Even exotic but natural states of matter like degenerate cores or regions of quark-like plasma change how energy moves through a star and how neutrinos are produced. Each of these is messy and technical but plausible, and none require an interior cavity carved by design. Still, the hollow interpretation is a powerful image. If a star actually contained an open interior or engineered space, the implication would be staggering. Ancient constructors with the technology to hollow a stellar mass or to build a cavity at stellar scales would be beyond anything human history can imagine. Such a claim moves immediately from astrophysics into deep philosophical territory about agency, longevity, and cosmic archaeology. That is why skepticism matters. Scientific method demands multiple independent lines of evidence and reproducible prediction. Extraordinary claims require not only unusual data, but also a robust pathway from hypothesis to test, and history is full of anomalies that surrendered to better models once new physics or better instruments arrived. Society's reaction to a persistent hollow hypothesis would be complex. Some religious communities might read the discovery into creation narratives. Some thinkers would frame it as proof that intelligence can shape stars over epochs. Conspiracy-minded groups would spin stories of hidden engineering and suppression of data. Scientists would push back with careful analysis and public discussions about uncertainty. Responsible science communication becomes crucial in that moment. Communicators must state what is known and what is not known. They must show raw data and error bars rather than dramatic assertions. They must explain how detector sensitivities, selection biases, and instrument noise can fool interpretation, and why replication across different observatories matters. Clear language about probability and about the limits of current models helps prevent panic and prevents premature heroization or demonization of the data. For storytellers and filmmakers, the visuals are irresistible and also instructive. Show an explained spectral graph where the missing lines are highlighted and compare it to a model spectrum so viewers can see the gap. Animate helioseismic maps like ripples on a pond, and then morph them to show how trapped modes would look if a cavity were present. Cut to short interviews with skeptical astronomers who point at alternate explanations and who walk viewers through the math in plain words. Overlay neutrino event plots and explain in narration how small deviations pile up into a signal that cannot be ignored. Emphasize the limits of the datasets by showing the sparse coverage of certain wavelengths and the old timelines of the most sensitive detectors. The largest point of drama is methodological. Current observations are intriguing but limited. What would it take to confirm or to debunk the hollow hypothesis? Would it require decades of helioseismic monitoring with higher fidelity to map every oscillation mode? Would it need multi-band spectroscopy from ultraviolet through radio to rule out strange atmospheric chemistry? Would it demand neutrino detectors with better directionality and lower backgrounds to pin down where the particles come from? Could long baseline interferometry resolve asymmetries in the star's surface that point to deep structure? Or would we need a probe that can ride into the outer layers to measure density and feel directly a proposition so difficult it currently sits in the realm of engineering dreams? The question remains open, and the answer will reshape how we read the light of stars across the galaxy. What combination of instruments and observations would finally close the case and tell us whether the hollow whisper is natural or an echo of something crafted long ago? Some belts shine like cut cathedral glass. In the glass garden system, whole asteroid lanes are littered with panes and shards carved not by hands but by fire. When massive rocks strike each other at orbital speed, the impact delivers forces and temperatures that melt silicate minerals into a molten soup. Under the right conditions, that melt cools so quickly and evenly that it does not have time to crystallize. Instead, the atoms lock into a disordered solid and glass is born. On Earth, tiny cousins of these fragments exist as tektites, rounded black beads flung from ancient collisions. But in the low gravity and vacuum of a belt, the molten spray can stretch into sheets and plates before it hardens, producing slabs of translucent glass that reach sizes no terrestrial furnace could match. The chemistry is plain and essential. High silica content makes the clearest panes, while mixes rich in iron and magnesium tint the glass darker or green. Volatile gases trapped during quench form bubbles and veins that scatter light, turning some shards into frosted panels and others into near crystal clarity. Shock pressures in an impact reach levels that compress and rearrange minerals, and temperatures surge into tens of thousands of degrees for brief instants, so the process is violent and brief and physically simple in its outcome. Nature becomes a giant glassworks. Harvesting that bounty rewrites industry in the system. Mining rigs do not dig so much as sculpt. thermal cutters and shaped charge arrays soften and peel layers, while robotic arms unfurl tensile frames to cradle enormous panes as they are rotated and polished in microgravity. Whole factories drift in the belt, their scaffolds anchoring to slow tumblers of glass that are then sawn into sheets and bolstered with composite ribs. Because the raw material is already glass, the energy cost of turning it into translucent architecture is far lower than smelting rock into metal and then refining that into building panels. Economies sprout immediately around orbital greenhouses that use these panels as their skin. Translucent domes let plants sip a precise mix of starlight and diffused glow, and they give workers an unbroken view of the galaxy as if gardens had been stitched into the heavens. The same sheets become panoramas for living quarters, bathhouses with a curtain of stars above, and public galleries where light itself is exhibited as medium and message. Architects learn to treat glass as both wall and lens. Structural frames carry bending loads while panels are laminated with tension woven into their edges, so a pane the size of a plaza can hold pressure and resist fractures. Photonic coatings tune which bands of light pass through, blocking harmful ultraviolet while channeling the red and blue bands that plants crave. Fiber optic veins embed into panes to carry power and information, turning windows into displays and conduits at the same time. A new aesthetic movement grows from this material reality. Designers and philosophers coin a phrase that becomes shorthand for a lifestyle: transparent living. It values openness in the literal sense and in social terms. Living rooms become observatories, and city planners curate sightlines toward constellations as civic heritage. Artists carve negative space into panels and carve light into architecture, using refraction to paint with the night. Markets form for bespoke panes that hold swirls of trapped bubble art or that tint like living skin as sensors modulate their hue. The system is not without trade-offs. Glass is brittle, and micrometeorite showers can nick or shatter panels, so redundancy and repair culture are central. Habitats develop rapid swap routines, and repair fleets trundle through orbital lanes like window washers. Privacy becomes a political and personal design problem. How do you live transparently beneath a cathedral of stars and also keep a private life? The solutions are inventive and tactile. Layers of electrochromic film darken at a thought when a circuit is closed, and liquid crystal interlayers scatter light into opaque patterns when voltage runs through them. Suspended lattices of polarized films block direct view while passing ambient glow, and retractable louvers fold like leaves to close off a room in seconds. Some communities embrace total exposure as a kind of communal honesty, creating neighborhoods where walls are almost all clear and privacy is managed by social norms and time sharing. Others turn toward hybrid practices with translucent public facades and secure private cores. Artists thrive in the middle ground. They etch microstructures into panes that bend starlight into private canvases visible only from particular angles. They compose performances where dancers move behind layered glass and the audience reads the choreography in shifting refractions. Scientists find unexpected value as well. Large clear panels double as passive telescope covers and as radiative heat dumps, and the optical purity of some glass makes it ideal for photonic instruments and for manufacturing long-distance fiber that links habitats across orbital lanes. The visuals of such a world are immediate and cinematic. Show a mining rig easing a plate free from a tumbling shard, saws glowing as they slice through translucent rock, robots polishing an edge until it gleams like a lake. Cut to greenhouse interiors where leaves sway beneath a ceiling that is the Milky Way itself, and let a time-lapse roll of molten glass forming and quenching across an impact flash so viewers feel the birth of panels in a single heartbeat. The final question circles back to human rhythm. Will transparent living remake privacy into a curated performance, or will people build inner sanctums hidden behind technological veils and social contract? How will artists exploit a sky that becomes a gallery? And how will managers of sunlight learn to harvest its heat and to spare the plants and bodies that need careful spectral balance? Would you prefer a home that opens to the cosmos, or one that closes and keeps the stars as a distant promise? Near a compact object, space itself can sculpt light into cathedral-like arches. Massive bodies bend the paths of light, so a distant star can appear smeared into an arc or wrapped into a ring, and those rings that encircle a dark core are the signature everyone points a telescope at. Think of a heavy stone sitting on a stretched sheet and imagine marbles rolling in curved tracks around it. Only the marbles are beams of light and the sheet is the fabric of space and time. When gas and dust spiral toward a compact object, they form a luminous disk, and that disk becomes a stage for remarkable optics. Hot plasma races inward, heating and glowing in X-ray and ultraviolet, while magnetic fields pinch material into jets that launch away along the poles. One jet aimed toward us looks brighter and bluer, the other aimed away is stretched and dimmed into red shifted light, and the pair together write a long-distance signature that betrays motion and gravity. Those features are not just pretty patterns in a telescope, they are maps of curvature, fingerprints that let astronomers measure mass and spin at immense distances. An Einstein ring marks when light from a background source is bent so symmetrically that it creates a halo, and small departures from symmetry reveal warped corridors where light has taken different routes and met itself again. Spectra shifted toward red tell us material is fleeing into the deep well. Spectra shifted toward blue show material racing toward us at relativistic speed, and timing variations in the light betray how time itself yawns under intense gravity. Time dilation is the deep, unsettling companion of that beauty. Clocks near the compact object tick more slowly compared with clocks far away, so a short visit at the inner edge could mean returning to a world that aged decades while you barely moved. That makes life near the cathedral emotionally intense. Ceremonies revolve around windows of synchrony when the time difference is small. Families schedule reunions in careful coupling with far orbit timetables. Artists paint with delayed light, composing performances that only resolve for audiences who have matched their watches to different gravitational heights. Engineers answer with structure and cunning. Permanent habitats cannot sit on the inner brink like boats on a shore. They must ride in stable niches where gravitational pulls balance into gentle, stable paths. Those Lagrange-like orbits are pockets where the pull of star and compact object and orbital motion form an uneasy truce. Here habitats hang in sky like suspended cathedrals, connected by tethered transfer lines and by vehicles that hop between equilibrium lanes. Deep well dwellings wrap themselves in heavy mass to block deadly radiation from the accretion flow, and they anchor superconducting coils that steer charged particles away from living quarters. Tidal forces still tug at everything, so designs favor flexible joints and segmented shells that can bend without shattering. Power is a central temptation and a central danger. A rotating compact object carries enormous rotational energy, and clever physics offers ways to steal some of that energy without plunging in. One strategy is a Penrose-like process, where carefully sent material extracts angular momentum from the spinning object and escapes with more energy than it began with. In practice, that means accelerating particles in engineered ergosphere zones and harvesting the excess as usable power. Another approach funnels infalling matter into controlled accretion segments that convert gravitational potential into heat and light, and then into electricity with extreme efficiency. Those methods promise energy densities beyond anything available from ordinary stellar farms, but they come with trade-offs. Manipulating flows at relativistic speeds increases the risk of sudden flares, and a miscalculation can hurl a plasma shock right into a settlement. The psychological landscape of residents is as warped as their sky. Streets curve into unexpected perspectives because light itself takes bent routes. so alleys can reveal multiple suns at once and doorways can frame shifted images of the same neighbor. An evening walk under the lensing arches is like moving through stained glass where reflections recombine in surprising places. People speak of temporal neighborhoods where clocks are intentionally out of step to create living time pockets, places to savor a slow afternoon or to compress work into short subjective hours. Children learn to read a watch not only for minutes but for gravitational levels, and storytellers compare love and loss across frames of reference. For filmmakers, the imagery is rich and immediate. Ray-traced lensing simulations let viewers watch a street transform as a massive object slides into view, turning familiar buildings into looping arcs of light. Interior concept art of warped city alleys can show lamps that cast multiple shadows, stairways that seem to climb twice, and windows that reflect events from hours apart. Citizen interviews make the idea intimate. An elder speaks of seeing a granddaughter twice in a single day because one stood at the rim and the other at the shelf of a deep well settlement. A technician describes the thrill of turning a Penrose-like coil and the dread of the emergency siren that means a flare will reorder a week in minutes. Those human moments fold the physics into daily life, but the promises of power and spectacle bring ethical weight. Mining a gravity well requires moving mass and angling flows in ways that can change the accretion structure and the long-term stability of the system. A settlement that draws too greedily could trigger greater flaring or alter the rate at which the compact object sheds angular momentum, with consequences that ripple across entire orbital communities. There is also the cost in human time. Workers who spend months at deep gravitational heights return to loved ones who have aged at a different pace, and whole social classes could form on the basis of how much gravitational time they are willing to trade for energy wealth. Is tearing a cathedral out of space-time worth the strain it places on bodies and families, and on the natural evolution of the system itself? Would a civilization that pays centuries of subjective life for terawatts of power still call itself humane? The choice sits like a question carved into stone, and the cathedral of warped light keeps holding its reflection up to any who would answer. Night after night, neon veils sweep across these worlds like a slow cosmic parade. The sky is not scattered with a few icy comets. It is threaded through with tails that glow as if painted by some alien neon light, long ribbons that sweep from horizon to horizon and reframe what a night can be. The color comes from chemistry and from light working on frozen things. When rare ices and halogen-rich salts are warmed and ionized by strong ultraviolet or by charged particles streaming from the local star, they do not simply vaporize. Their atoms and molecules glow in very particular bands of color. Sodium-rich compounds give warm gold tones, potassium and certain organics throw deep violet and magenta, and ionized halogen mixtures can fluoresce in sharp greens and turquoise. In one plausible recipe, a comet carries a core of frozen water and complex hydrocarbons coated in layers of halogen salts and metal vapors. As it nears the star, its surface sublimates and a thin plasma sheath forms. That sheath is like a tiny glowing lamp whose emission lines light the tail and make it visible across great distances. In some variants, the glow is enhanced by microscopic dust grains that act like tiny fluorescent bulbs, absorbing energetic light and re-emitting it at visible wavelengths. Spectroscopic fingerprints tell the story. When a spectrograph splits the tail light into a rainbow, the result is not a smooth gradient but sharp, bright lines where particular elements announce themselves. Close up, those lines look like the ringing notes of a chemical orchestra. The composition hypotheses are exciting because they point toward resource flows as well as spectacle. Halogen salts are useful in industry and in medicine. Volatile organics feed fuel and polymer chemistry. Water always matters because it frees life from immediate dependence on hydrogen carried across long distances. A system rich in cometary volatiles becomes a natural supply chain that can support outposts, ships, and farms. How does a system become a neon comet field? The dynamics are part accident and part cosmic bookkeeping. A dense reservoir of icy planetesimals in the outer system is the seed. If a giant planet sits in a position that nudges passing objects inward on a regular beat, or if a distant stellar companion tips the outer cloud with periodic perturbations, then a steady trickle of comets will be sent inward. Add a compact inner architecture that scatters comets into eccentric, sun-grazing orbits, and you get nightly shows. In some systems, there are thousands and thousands of small bodies on eccentric paths, so tails are not rare surprises but nightly phenomena that cross planetary skies with predictable frequency. That predictability is what rewrites culture. People here learn to live with the parade. Entire lifestyles grow up around following and reading tales. Itinerant communities travel along mapped comet tracks in light craft and caravans, keeping just far enough to harvest volatiles as a comet sweeps past and close enough to feel the color wash across a camp. Seasonal migration festivals form around moments when the densest swarms pass closest to inhabited belts. These festivals are half harvest and half ritual. Tents and plazas fill with traders who buy comet distilled water and halogen salts. Musicians imitate the long draw of a plasma tail, and dancers wear suits layered with reactive materials that flash the comet's colors in time with the sky. Commerce becomes creative and risky. Tail skimmers ride the skirts of comets in tethered craft and pull thin filaments out of the coma into condensers. Those filaments are then processed on board into concentrated volatiles. Large harvesters trail behind clusters in slow rendezvous and use electrostatic nets and cold traps to snag dust and condense gases. Architects and engineers design portable refinery rigs that lock onto a passing tail, process a harvestable fraction, and then release the skimmer to ride the next rendezvous. That business model favors mobility and repair skill over heavy static infrastructure. The romance of neon nights coexists with practical danger. Tails are made of dust and ice moving at orbital speeds that can be tens of kilometers per second relative to a settled outpost. Even the smallest micrometeorites carry crushing energy. Impact risk is not hypothetical. Settlements and caravans face steady erosion and the occasional catastrophic strike. Communities respond with layered defenses that are as much cultural as technical. Buildings and ships carry sacrificial outer skins, composite sheaths that vaporize incoming particles and spread their kinetic energy. Engineers repurpose a technique that old spacefarers used, the Whipple shield, building multi-layer barriers that fragment and slow impacts before they hit critical systems. Magnetic deflectors run as long loops around large ports to steer charged dust away, and active plasma coils smooth flows of ionized material into predictable lanes. Navigation becomes a practiced art. Chart makers publish comet calendars and high-fidelity maps showing expected tail density, ionization state, and safe approach vectors. Pilots learn to read faint spectral cues that indicate a tail as composition, and therefore its abrasivity or stickiness. Communities also build physical infrastructure for safety. Harbor rings take the form of rotating barriers that sweep a safe corridor like a mechanical broom. Underground shelters and retractable domes give quick refuge during sudden spikes in tail density. Ritual-fused days become normal. Schools teach children how to read a tail the way sailors once read wind and swell. For creators, the visuals are cinematic. Long time-lapse sequences can show an entire night as ribbons of neon travel and cross like cometary highways. A close-up spectrograph shot can morph a line of color into its elemental identity so viewers can feel chemistry as color. Festival reenactments layer human music and motion over real tail footage to give scale and heart. Cut from the wide neon arcs to the gritty intimacy of a skimmer crew bracing as particles ping an armored hull, and to technicians patching a composite skin with practiced hands. Living with the neon sky is a choice between embrace and caution. Communities who follow the trails gain water and wealth and wear the colors of the sky on their clothes. Those who hide under heavy shields save lives and years of maintenance. Either way, the culture learns to engineer around the risk. They build layered shields and mapped lanes, and they prize the skill of reading a comet's mood as much as any seafarer once prized the way of wind and tide. A star can be a maze. Here the protoplanetary disk is not a smooth sheet of dust and gas but a carved landscape of rings and spiral corridors sculpted by planets on the move. Migrating worlds act like slow plows and shepherds. As a forming planet pushes through the disk, it exchanges angular momentum with the surrounding gas and dust, and that exchange nudges the planet inward or outward over time. Small planets slide through the disk more easily and drift like leaves on a current. Larger worlds carve deep lanes and open gaps as they sweep up or scatter material. The gravity of a migrating planet launches spiral density waves through the disk, the same way a boat leaves a wake across water, and those waves concentrate or evacuate dust into sharp bands and resonant gaps. Left alone, those patterns smooth out, but when multiple planets move in concert, they lock into resonance chains where each orbit matches a simple ratio with its neighbor, and the maze becomes both stable and finely detailed. Shepherding effects add another layer of craftsmanship. A planet can trap smaller bodies in its wake like a shepherd corralling sheep, holding them in narrow corridors called orbital lanes or feeding zones. Those trapped particles collide and grow or, if disturbed, spill out and feed the next wave of planet formation. The result is an intricate lattice of calm pockets and turbulent passageways that record the planet's past migrations and encounters. Some of the clearest real clues come from high-resolution images of young systems. The photographs of H.L. Torrey stunned astronomers because they showed rings and gaps in a star system that was still very young, suggesting that planets can carve majestic structure far earlier than we once expected. Those rings and gaps are the fingerprints of migration and resonance, and they let researchers read the timeline of formation like pages in a book. Observers can measure the sharpness of a gap to estimate a planet's mass, trace spiral arms to infer migration speed, and map asymmetries that hint at past collisions or hidden companions. For astronomers, the labyrinth is both archive and laboratory. Watching a disk with time series observations reveals motion and change. A spiral arm that drifts outward signals outward migration. A vortex growing at the edge of a gap shows where dust piles up and seeds new planets. Each corridor, each calm pocket, is a clue about forces that acted long ago and about the rules that govern birth and growth of worlds. For people who would live inside such a system, the maze opens practical possibilities and poetry alike. In the quiet, stable gaps between rings, there are places where relative velocities are low and dust storms are gentle enough to anchor habitats. Those niches could host tethered ring colonies or modular platforms that harvest raw material from passing streams of pebbles. Settlements would be engineered for fine control over incoming dust, with magnetic dust catchers and sacrificial outer layers that peel away and are replaced like bark. Transportation through the corridors becomes a new art form. Imagine magnetic sail craft that unfurl broad electromagnetic fields to ride charged particle flows and density waves like skiffs on a luminous river. Pilots trim field geometries to skim close to a spiral wall and then crest a calm gap with a whisper. Tourism would thrive on guided passages through dust lanes where light scatters into amber fog and where every bend frames a different star side. Operators would sell slow expeditions that drift along spiral arms at safe distances, soundtracked by filtered radio echoes and lit by the diffuse glow of illuminated dust. There is a deep romance to exploring a stellar maze. Walkways on a settlement rim could open onto a corridor where dust drifts like snow and where you can watch the carved face of a nearby planet like an artisan at work. Artists would paint with dust, choreographing floating festivals that send glittering streaks across a corridor for a single orbit and then let them vanish. Scientists would lead night tours and explain how a particular gap preserves the memory of an early close encounter. the visual potential is immense. High-resolution images from the Atacama Large Millimeter Array reveal rings like frozen ripples and serve as the perfect base for animated migration sequences that show planets sliding and gaps deepening. A simulated fly through a spiral corridor can turn abstract dynamics into visceral experience as viewers watch dust lanes close in and then part under a passing magnetized sail craft. Virtual tours that stitch actual observations with modeled motion let an audience wander a labyrinth that shifts over centuries in seconds, and a provocative question hangs over the whole idea. If planets can carve readable patterns into disks, might an advanced civilization sculpt dust and gaps intentionally to send messages or to mark territory visible across interstellar distances? Could a deliberate arrangement of rings and spirals be a beacon written in sand and stone on a cosmic scale? If you could pilot a sail craft through those corridors or stand on a calm gap and watch a planet carve another pass, what message would you hope to find etched into the maze by a mind not like ours? Some relics orbit like sleeping cities. Out beyond the last mapped cluster, there is a system where ruins drift in patient formation. A bazaar of hollowed habitats and inert starships arranged like relics on a slow celestial carousel. The site at first looks like ordinary debris, but patterns emerge as you watch. Modules fall into repeated spacing as if set on invisible racks. Entire rings of structure share the same inclination and eccentricity, and a handful of hulks trace mirror images of one another the way market stalls line a winding street. Those regularities are the first whisper that something deliberate shaped this place. Telescopes and probes add sharper clues. Spectral scans show metal alloys in proportions strange to natural condensation, materials that absorb and emit light in narrow lines typical of processed compounds and engineered polymers rather than raw rock or ice. Radar and LiDAR mapping returns flat planes and right angles, repeating geometric motifs no impact field should produce. Radio surveys find bursts that sound like delayed pings and structured prime sequences folded underneath the noise of cosmic background. Put these signs together and you get a language of evidence that reads like a civilizational footprint. Scientists call the field archaeoastronomy. The tools are familiar, but the rules change on a cosmic scale. Researchers debate how to interpret each data point because natural processes can sometimes mimic order, and because the stakes are not simply intellectual. If these are remains of a vanished species, then every artifact is a rare library. The salvage argument sounds practical and generous. Harvest the housings and drives to learn manufacturing techniques that could leap us forward. Reclaim storage tanks and radiators that contain water and metals. Extract information from frozen data caches and speech cores and use those discoveries to cure disease, to build cleaner reactors, to unlock new ways to travel. Opposing that view are voices of restraint. Preserving the site is a form of cosmic respect, an ethical stance that a dead culture deserves time to be studied without being broken for parts. Out of sight of Earth, the analogy to terrestrial tombs and sacred sites becomes immediate. Archaeologists point to past mistakes where hurried looting erased context and turned a record into raw goods. There is also a practical risk that salvage unwittingly corrupts fragile records and contaminates dormant biosignatures with our microbes. If even the faintest trace of life remains in suspended animation, waking or disturbing it without consent becomes an act with moral weight equal to violation. The legal landscape is messy. Current treaties about space heritage are thin and loosely enforced. Nations and corporations make competing claims under different interpretations of salvage rights, and private off-world firms already draft contracts that promise clients a share of recovered goods. Proposals for a planetary heritage designation compete with arguments for free resource access. Should ruins in orbit be declared a protected site like a marine reserve, policed by an international coalition, or are they fair game for whoever reaches them first and can pay the crews that pry them loose? Where law and ethics are slow to act, a black market finds its niche. Salvage runners skirt official channels, slipping into shadowed lanes between observation gaps and selling shards, art objects, even data fragments to collectors who prize the exotic. Smugglers advertise fragments of alien fabric and engraved plates as status pieces. That commerce is small and secret but corrosive. Once a single unique artifact becomes a commodity, its context is ruined forever. Worse still, clandestine teams may attempt to open preserved habitats in search of valuables or biological samples and bring home unknown pathogens or technologies they barely comprehend. The cultural fascination is unstoppable. Ghost stories bloom. Artists and musicians tour the digital scans and compose pieces out of the measured squeal of an airlock or the thermal sigh of a dead hydroponic array. Pilgrims sign up for sanctioned viewing runs to float near a ring of sleeping towers and to feel the hairline echo of someone else's infrastructure. Philosophers argue on panels about the rights of the absent. Is a civilization beyond death still owed the same protections we give to ancestral graves? Some communities say yes and demand strict preservation. Others claim that recovery is a moral good because knowledge can save lives. There are difficult technical questions as well. How would we detect true biostasis? Tiny thermal gradients or faint chemical disequilibria could be the difference between a storage module and a living tomb. Opening a habitat risks exposing dormant microbial ecosystems to oxygen-rich environments and to new biochemistry for which they have no defenses. At the same time, leaving them sealed could mean losing information if slow decay erodes fragile data media. Engineers and ethicists sit in long meetings trying to design protocols for sampling that minimize risk while maximizing knowledge, a balance that tests both patience and nerve. The human stories are raw and cinematic. Imagine a quiet port where an artist unfurls a canvas painted with the recorded light signature of a derelict plaza. Picture an international court where jurists speak for the future of heritage protection, and where corporate lawyers argue that a recovered reactor could end dependence on scarce fuels. Envision a dim warehouse in a far orbit where a recovered ceremonial object glows under illicit halogen lamps as a buyer places a credit through an encrypted channel. Those images are not hypothetical. They are the social weather that shapes policy and the culture that surrounds discovery. Visuals for a creator are easy to sell to the imagination. Render derelict habitats rotating slowly with frost blooming at seam joints, their bay doors scabbed shut and their nameplates pocked by micrometeorites. Make scans that pull away layers to reveal repeating frames and modular geometry like a mechanical market whose stalls form concentric arrays. Stage courtroom-style debates in a cold hall lit by spectra plots projected on a wall, voices arguing about custody and conscience. Cut to a shadowy salvage crew carefully slicing an outer skin with plasma cutters while a child on a viewing deck watches through a reinforced viewport and asks whether the dead would mind. The question returns again and again and gets sharper the closer we get. If sleeping minds do lie within those holes, awakening them is not merely an act of science. It is the most consequential conversation across time. To wake is to give agency and to risk shock and cultural collision. To fossil hunt is to turn memory into material and to make the vanished into fuel for the living. Both choices carry beauty and cost. Do we awaken or fossil hunt the sleepers? Two worlds clasped like dancers can share more than gravity. They orbit so close that the line between planet and moon blurs, each the size of Earth and each tracing a tight, mutual path around a common center. The pull they exert on one another stretches rock and ocean into long tidal bulges. Those bulges flex the crust and squeeze planetary interiors, turning orbital motion directly into heat. In places, the heating rivals the output of Jupiter's moon Io, producing localized hotspots of volcanoes, steam vents, and persistent tectonic churn. Because the energy comes from tidal work rather than internal radioactive decay, the activity concentrates where the pull is strongest, along facing hemispheres and at points where bulges drive massive stresses. Roche dynamics sets the limits of their embrace. If two worlds draw too close, the stronger tidal field begins to tear material from one to the other, or to launch debris into shared rings. Just outside that destructive boundary, the system is a sweet spot for drama. Tidal locking is almost inevitable. Each face points toward its partner so that one horizon always shows the twin world hung like a second sun, and the opposite horizon opens to darker space. That fixed view sculpts winds and currents. On the near sides, the constant gravitational tug raises seas and thins crust, creating warm coastal belts and volcano-dotted archipelagos. On the far sides, thicker lithospheres and calmer oceans can harbor slower climates and different biome strategies. With both planets locked, their climates fall into rhythms that mirror one another. When one world S-bulge rides highest, the other S-bulge does as well, and the shared tides rise and fall like a mutual heartbeat. Those mirrored geologies make mirror ecosystems plausible. Shorelines facing each other become ringed with tidal marshes that are alternately baked and drowned, breeding grounds for plants and animals adapted to extreme cyclical stress. Inland plateaus on each planet experience episodic volcanism that fertilizes soils in matching belts, so flora and fauna that evolve on opposite worlds can echo one another's S-forms. Migratory species on both planets might time movements to the same orbital phase, flaring across continents at matching seasons because the gravitational clock drives food web cycles in sync. Evolution takes parallel paths under parallel pressures, producing curious convergences that make naturalists on one world study the other, as though reading a parallel experiment. Human or intelligent cultures on twin-tide worlds arrange life around the dance. Calendars lock not to a distant star but to the mutual orbit and to the rhythm of tidal bulges. Festivals erupt at the moments when the two faces align and the seas reach a tabletop crest across both worlds. Navigation borrows the other world as a giant landmark. Sailors and pilots steer by the fixed outline across the sky, using the twin S-familiar mountain silhouette as a guide through storms. Short interplanetary trips resemble long ferry rides. Transport craft hop across the narrow gap in hours or days rather than months. So diplomacy and commerce become immediate neighborship. Embassies do not cross light years. They share lanes and coordinated docking times, and treaties read like municipal agreements more than distant statecraft. Social life is shaped by that closeness. Families spread across the pair keep real-time contact with tidal clocks and with scheduled ferry windows. Lovers exchange visits timed to orbital alignments when the gap narrows and gravitational tides calm for a predictable interval. Rivalries flare where resource-rich coasts face one another. Claims over a particularly productive tidal reef or a string of volcanic islands become matters of civic law and of ritual. Shared rituals also blossom. Twin beach festivals become choreographed spectacles. At alignment, the two planets might light beacons along matched shores, release synchronized floats, and sing songs that carry across radio and light so people on both planets can celebrate as one. Architects design piers and harbors to point toward the twin partner, and ceremonial plazas are aligned to frame the other world like a living painting. The practical realities are just as compelling. Energy systems harvest tidal work as a resource. Giant turbines anchored in connecting streams convert mutual tides into steady power. Transport corridors use gravitational assists to slip cargo between worlds with minimal fuel. And navigation becomes an art of timing curves and phasing, where a misstep can strand a freighter in a sudden surge or a sheltered inlet. Visual storytelling here sings. An animation that shows the slow, elegant orbital embrace gives viewers the sense of weight and timing. Cross-sections of tidal bulges reveal molten veins and convective pockets lighting the interior. Scenes of twin beach festivals with lanterns and aligned fireworks stitch human scale to planetary spectacle and hint at the awkward romance of seeing home and neighbor at once. Would you pledge allegiance to one shore or take a passport stamped by both planets? Which life sounds richer, the one that shares its sky with a beloved twin, or the one that trains its people to navigate constant gravitational intimacy and political twinship? A desert glows like a sapphire sea, wind sculpts dunes that shimmer in slow blue waves, and the light itself seems to be painted rather than reflected. Up close, the grains do not look like ordinary quartz. Some glitter like tiny chips of lapis or azurite with a cobalt tint, while others glow with a depth that feels structural rather than pigmented. The color can come from ordinary mineral chemistry, for example from cobalt-rich compounds, or from inclusions of minerals that absorb other colors and scatter blue. It can also arise from structural color, where the grain's internal architecture is a repeating pattern at the scale of visible light. That kind of structure sorts wavelengths by interference and scattering, so the blue you see is not a dye but a sorting of light itself. Both origins are plausible in planetary geology. A planet whose surface chemistry is rich in certain metals and silicates can produce sands tinted by real pigments. Impacts and volcanic ash can concentrate exotic minerals into dune fields. The more exotic route looks like opalization on a planetary scale. Tiny silica spheres pack into lattices and lock light into shimmering bands. On Earth, opal makes flashes of color because of that sphere packing. On a larger scale, similar photonic crystals embedded in sand grains would produce an intense, consistent blue as sunlight interacts with the regular spacing inside each grain. That blue changes everything about temperature and weather. A bright blue surface can reflect a lot of visible light, and that tends to keep daytime temperatures lower near the surface. But the same grains may absorb strongly in the infrared where the star's heat lives. The result is a paradox. From a distance, the dunes may look cool and reflective, but on the ground a thin layer can trap warmth and re-radiate it back at night. Fine powder settles into a near-insulating blanket, reducing thermal conduction into the subsurface and amplifying diurnal swings or smoothing them depending on grain composition. Wind-blown blue dust can drive microclimates across the basin, shading valleys and focusing heat on exposed ridges. The dunes themselves act like mirrors tuned by chemistry and by grain size, so a little change in particle packing or in the mineral mix can flip a slope from bright to brooding. Those photonic properties make the sand itself a resource. Fields of structurally colored grains become raw material for photonics, for pigments that do not fade, and for jewelry that literally sorts light. Harvesting operations use gentle collectors, electrostatic separators, and micron-scale sieves to pull out photonic-grade grains without grinding away the structures that create the color. Refineries then wash and stabilize the grains and assemble them into panels and coatings that can tune building light without power, or into optical components that use passive interference to guide and filter beams. Artisans turn polished grains into filigree and inlaid jewelry that carries living color without pigment degradation. An economy forms around careful extraction and stewardship because damage to the grains destroys their value. Daily life on the dunes mixes sport and caution. Dune surfing is a local obsession. Boards are broad and low to ride across powdery blue waves, and pilots wear layered suits that sacrificially take abrasion while sealing out fine grit. Goggles use polarized and spectrally tuned lenses to reduce glare and to sharpen horizons that can wash out under intense blue scatter. Footwear grounds static and vents charge dust away because fine photonic grains can build surprising electrostatic charges when blown and rubbed together. Settlements cluster near vegetated oases where native flora stabilizes edges, and harvest camps live on carefully timed rotations to avoid destabilizing wind corridors. Culturally, the blue sand is woven into identity. Markets trade beadwork and filigreed amulets cut from the rarest grains. Festivals sweep dunes with rituals that groom patterns into the ripples and then let the wind rewrite them, honoring both human craft and the planet's appetite for change. At the same time, conservation groups warn that strip harvests can collapse dune scaffolding and turn living gardens into dust. The politics of use and preservation follow the same rhythms as the tides did on twin worlds. Choices about who may take which dune become as contested as claims to fertile coasts. For a creator, the images write themselves. A drone slice sweeps low over a sea-sized basin of blue, moving like a skater through liquid light. Cut to microscopic footage where each grain looks like a tiny manufactured cathedral, a lattice of spheres or a crystal fleck reflecting a private spectrum. Show a workshop where a jeweler polishes a single grain into a pendant, and then a stadium of dune surfers launching from a ridge as powder sprays like blue mist. Close-ups on protective gear and on hands that turn raw sand into inlay make the human scale real. There is a story that travelers tell about a famous explorer named Imani Cade who crossed an entire sea-sized basin of blue sand on foot, hauling a solar lighter and a single crate of water. She spoke later of a silence that changed her sense of time, and of a far shore whose dunes were older and deeper than those she left behind. What did she find when she reached that distant rim? And why did she keep the small polished stone she carried home in her palm for the rest of her life? Night can become an absolute void of light. On a tidally locked world, the dayside bakes under constant sun, and the night side falls into unbroken shadow. In the glassy black ocean system, the darkness is not a trick of angle but a physical abyss that swallows photons. From orbit, the night side looks like a matte wound in the planet's skin, a liquid sea so dense and so absorptive that mirrors and stars vanish into it. Up close, the surface moves like molten pitch, slow and viscous, and it gives nothing back. No reflection, no glint, only a hungry black that seems to drink starlight and keep it. How could something like that form? One idea is chemistry driven by extreme pressure and exotic bonding. Under high pressure, simple molecules can polymerize into long-chained networks that flow like syrup but behave optically like glass because their internal structure traps light. Another route is particulate loading, where a sea of fine carbon-based soot and metal flakes suspends in liquid, creating an almost perfect absorber across visible and infrared bands. A third possibility is a surface made of metamaterial-like patterns on a planetary scale. Metamaterials are structures engineered at tiny scales to guide and trap light in ways ordinary matter does not. If a planet's surface was strewn with sheets of microscopic geometry, or with layered shards that act like one-way mirrors, then incoming light could be bent and scattered until it never escapes. Each hypothesis has different consequences for how heat moves through the world. Heat transport is the planet's invisible drama. A pure absorber will gain internal energy when light hits it and convert that energy into heat. If the black ocean also irradiates efficiently in thermal bands, the night side could release that heat back into space and stay relatively cool. If instead the abyss traps both visible and thermal photons, then heat builds and the night side becomes a slow, smoldering ember below the void. Either way, the gradient between the endless day and the absolute night drives savage weather along the terminator, the narrow ring where star and abyss meet. Winds race from the hot face to the cold and then curl into jet streams that shear along the horizon. Ocean currents under the black surface would still move, carrying heat toward or away from the interface in waves the eye cannot see. Tidal flexing from the star tugging at the planet's body can stir the abyss into sloshes that last for hours and days, and rock warmed by those motions can vent through fissures as faint thermal plumes. Humans or any settlers would treat the terminator like a frontier and a power plant at once. The thermal contrast is a resource. Engineers would build heat engines that run like great atmospheric turbines between the hot day sky and the cold black sea. Thermoelectric arrays and closed-cycle engines could pump heat from one zone to another and generate electricity without burning fuel. In places, the gradient is predictable enough to schedule large-scale power runs where turbines spool up as a storm front crosses and then idle during calm intervals. Mirrored daytime shields will be deployed above agricultural belts to reflect excess light and to channel heat away from living quarters. Those shields are not passive roofs but adjustable sails and louvers that tune how much star hits a field, making the dayside into a set of controllable climate gardens rather than a furnace. On the night side, exploration depends less on light and more on indirect senses. Optical instruments fail against an honest absorber, so probes rely on gravimeters that sense small mass anomalies, on acoustic arrays that listen for subsurface movement, and on synthetic aperture radar that returns structure beneath layers that swallow light. Submersibles carry their own low-frequency sonar and thermal probes, and they map a black sea in gradients of pressure and warmth rather than in images. The abyss shapes culture as much as technology. Myths grow easily where sight cannot go. People who live along the edge tell stories of a throat of night that swallows names and of a city of lost lamps lying under the glass. Some faiths treat the ocean as a living being to be placated with offerings cast at the terminator. Artists develop a language of absence. Painters learn to carve negative space into rituals and to use faint thermal paints that glow only when a hand warms them. Poets write about a darkness that returns your secrets rather than your face, and children play games of whispering toward the black, knowing that their voices will not come back the same. The aesthetic is not simply fear. Many practitioners find serenity in the depth of absolute black, composing music whose tones are arranged to match the slow shudder of the abyss under tidal stress. For creators, the visuals are striking and eerie. Heat maps that smear like weather charts show the sharp contrast between day and night. A simulated traverse across the black ocean can cut to a probe's perspective as its optical cameras go dead, and a chorus of sonar pings and thermal spikes paints a ghostly contour. Indigenous art sequences can be woven in to show how absence became ornament, with tapestries that darken when the viewer's palm passes, and with murals that only reveal form under ultraviolet pass-through special filters. Close-ups of mirrored shields rolling out like petals and of turbine farms perched along the terminator bring technology and myth into the same frame. And the final question hangs heavy above all the images. If you could drop a probe or a suit into an ocean that swallows light, what would you expect to find beneath the surface that gives nothing back to the sky? And would you have the courage to dive into a place that keeps its secret so completely? Seasons break when the star itself skips a beat. Some stars are steady clocks and others are temperamental singers. Flare stars are small, cool stars whose magnetic fields twist and snap and then fling out sudden bursts of light and charged particles. T-Tauri stars are newborn suns still feeding from a surrounding disk, so their brightness can wander wildly as accretion streams flare and falter. Both kinds of variability matter because a planet's climate reads the star's mood like weather. A sudden flare can shower a world with ultraviolet and energetic particles and warm an atmosphere for minutes to hours before it collapses back, while longer-term accretion swings can raise or lower average luminosity across seasons that last months or years. When that timing is irregular, the planet does not get a predictable cycle of spring and winter. Instead, life faces a series of surprise summers and unannounced freezes that arrive with no calendar warning. Ecosystems respond in striking ways. Plants and microbes evolve fast-triggered life cycles that can bloom, seed, and hide in hours or days, or they adopt extreme dormancy where metabolism slows to a trickle until the next favorable window. Animals and complex organisms favor flexibility. Generalist feeders and migratory strategies dominate because specialization becomes a liability when the table of food can vanish overnight. Evolution often tilts toward redundancy, toward multiple fallback pathways for growth and reproduction, and toward tissues that repair radiation damage quickly because stellar tantrums bring high-energy bursts. Human survival adds technology and ritual to biology. Flexible agriculture becomes a craft of movable farms and layered greenhouses. Farms sit on tracks and barges and in inflatable arcs so they can be relocated into sheltered valleys or spun into artificial night during a flare. Crop mixes are deliberately diverse with fast-growing staples and slow-maturing backup strains. Cryogenic seed banks and spore vaults hold living libraries in chilled stasis for seasons when surface cultivation fails. Engineers build thermal inertia into cities with stone and water reservoirs that store heat from brief warm spells and release it through long freezes. Shielding is standard and modular so a community can close down like a clam when the star flares and then reopen to catch a sudden sunny window. Culture reshapes itself around unpredictability. Rituals become practical. Festivals mark the first safe day after a freeze and include communal checks of stores and equipment. Storytellers teach children to read subtle sky cues and to memorize contingency songs that encode cultivation sequences for the next short warm pulse. Some societies formalize randomness into law with rotating crop shares and time banks that spread risk across neighborhoods. Scientists and ecologists model these systems to find resilience pathways. Visuals worth showing include dramatic before and after seasonal maps that flip in an instant from green floods of life to frost-covered plains, and time-lapse recreations of a flare-s impact where forests burn bright in ultraviolet and then regrow from buried seeds that germinate when the flux subsides. Interviews with modelers can show probability maps of habitable windows and explain how a biosphere-s recovery time compares to a typical flare cadence. Footage of farmers pulling mobile greenhouses like wheeled gardens and of technicians lifting frost-sealed vault lids to inspect a single precious seed make the stakes human. The deep question is whether chaos breeds strength or keeps complexity from taking root. Does repeated surprise harden life into resilient networks that can survive anything, or does it punish long-lived, delicate systems and lock a world into forever simple cycles of boom and bust? Some landscapes act like cosmic furnaces. In the Obsidian Gate system, massive impact basins fused into glossy, glass-lined craters that behave like natural concentrators of sunlight and heat. During a cataclysmic strike, the crust melts into rivers of molten silicate that coat a basin with a polished, vitrified skin. As that skin cools into glass, it can form smooth, concave surfaces that reflect and focus incoming light while its dark, low-albedo face soaks up any stray photons that miss the focal point. The geometry is the secret. Steep walls and nested bowls guide rays toward predictable hotspots where sunlight and thermal emission concentrate into persistent plumes of heat. Those plumes are not random. Orbital tilt and the crater S-shape lock the pattern into a clockwork so engineers can forecast when and where the glare will peak and where thermal gradients will be steepest. Composition matters too. The obsidian-like glass is dense and relatively non-porous compared with fragmented regolith, so heat flows more cleanly into the subsurface. Continuous glass and fused rock act as thermal highways that carry surface energy down into buried reservoirs and into engineered heat exchangers. That combination of focused radiation and predictable conduction turns each gate into a reliable, high-density energy source, ideal for industrial processes that crave sustained high temperatures. Industries that sprout at these gates feel elemental. Steel and glassworks that would be impossible on a temperate plane set up mirror farms and trough fields that steer sunlight into central absorbers. Thermochemical reactors run on gate heat to split water into hydrogen and oxygen without vast electrical input. Smelting and material synthesis exploit the steady furnace to melt refractory ores, and complex manufacturing clusters chain processes together so waste heat from one plant feeds the next. The economy concentrates because moving raw materials to a hotspot costs less than recreating those temperatures elsewhere, and so whole city-scale works arise on the rims and slopes. Life in those hubs is shaped by both rhythm and reverence. Workers time their shifts to the gate S-cycle and neighborhoods cluster on the safe periphery. Communities develop rituals tied to the day when the crater flares brightest. Pilgrims ride long routes to stand at sanctioned viewing platforms and watch the gate bloom like a man-made sun. Some cultures consider the gates sacred thresholds between the living planet and a world of pure energy, and ceremonies mark rites of passage with heat-lit torches and songs composed to be heard above the hiss of steam. Governance and guardianship often become part of the law. Gatekeepers manage access, calibrate reflectors, and arbitrate who may tap into the concentrated flux. The romance of focused energy sits beside harder realities. Concentrating industry in geological singularities risks tipping localized climates. Endless heat funnels alter wind patterns and create rising columns that draw in dry air from far away, potentially desiccating neighboring biomass. Waste heat and aerosols can seed new cloud regimes, changing precipitation downwind and stressing ecosystems that evolved under different conditions. If harvest scales without restraint, a slow feedback can form where warmed rock releases trapped volatiles, which then amplify greenhouse effects and expand the hot zone beyond the original crater. That expansion can strand communities and erase heritage sites as the gate grows into a molten frontier. The engineering responses are inventive but imperfect. Thermal shutters, adaptive reflectors, and staged extraction systems try to modulate output so heat is drawn only when needed. Subsurface reservoirs store excess warmth for off-cycle use and reduce instantaneous flux to the surroundings. Environmental buffers, protected belts of flora, and legal limits on extraction attempt to put guardrails around the temptation to squeeze every watt from a gate. The tension between necessity and preservation becomes a social fault line. Visual storytelling sells the contradiction. Thermal renderings that paint heat funnels in living color show how energy flows from sun to hotspot and then into a factory spine. Mining colony concept art places terraces and piping like veins around a black bowl, workers in reflective gear moving under a sky lit by focused glare. Infographics that diagram energy flux funnels make the predictability tangible and let viewers see where power is harvested and where waste heat spills. Close-ups of polished glass cliffs and of mirror fields bending light into a narrow seam bring the physics home. The ethical question is sharp and unavoidable. Do we concentrate civilization as most intense heat into unique planetary features to unlock rapid industrial growth? Or do we treat those gates as geological wonders to be curated and protected for their rarity and ecological fragility? Some worlds blur the line between particle and wave. In the quantum fog realm, the clouds do not simply scatter light. They split it into interference tapestries that make the land shimmer like layered photographs that refuse to settle. A ridge can appear twice at once and then fold back into a single outline as if the scene is trying on different versions of itself. Artists call it a living hologram, and scientists call it a hypothesis that must survive the harsh language of experiment. The idea traces back to familiar quantum effects and then stretches them into the speculative. On Earth, interference and superposition are everyday words in laboratories. Superposition means a tiny object can exist in several states at once until it is measured, and interference is the pattern that appears when two wave-like possibilities overlap and reinforce or cancel each other. We see interference in ripples on a pond and in bands of color from thin oil films, and in the lab we coax electrons and atoms to show similar patterns when we keep them cold and quiet. Those lab successes matter because they tell us two things. One, macroscopic quantum behavior is real when systems are very well isolated, and two, maintaining that coherence becomes almost impossible once thermal noise and collisions kick in. The quantum fog realm asks a bold question. What if nature found a way to hold mesoscopic coherence at planetary scales in very special pockets of atmosphere? The speculative routes are specific and demanding. Extremely low temperatures reduce thermal jostling so particles do not quickly lose their phase. High vacuum and minimal particulate collisions stop environment-driven decoherence that would otherwise scramble delicate phase relationships. Coherent matter phases such as Bose-Einstein condensates where many particles share one quantum state could, in principle, form extended clouds if the chemistry and pressure cooperate. Superfluid-like behavior and long-lived topological order are other candidate states because they protect phase information from ordinary disturbances. Add strong magnetic or electromagnetic ordering that couples wide regions together, and you can imagine phase locking across kilometers rather than microns. None of this is easy. Every extra degree of warmth, every stray photon or cosmic ray, every gust of turbulence is an enemy of coherence. That is why the hypothesis stays in a careful speculative room rather than marching straight into fact. Still, the possible phenomenology is rich and strange. A quantum coherent cloud could act like a slowly shifting diffraction grating, sending interference fringes across valleys and folding distant horizons into double exposures. Light passing through these clouds might show narrow bands of enhanced brightness where waves reinforce and pockets of silence where they cancel. Because quantum phases can carry subtle correlations, two distant observers might see related patterns that shift in lockstep, creating uncanny synchronies between places that otherwise feel separate. Life living under such skies would adapt in unexpected ways. Artists would shift from pigment and stone to phase and timing. A new craft would arise that sculpts patterns by nudging phase boundaries with heat flares, guided electromagnetic pulses, or timed flocks that scatter the fog in controlled sequences. Composers would write pieces that only resolve when viewed from particular vantage points where interference lines cross. Architects might design public plazas as instrument panels where people move to tune the scene and to produce living images that resolve and collapse on command. Even belief would rearrange itself. Religions and philosophies could take the metaphor of superposition seriously and weave it into ethics about choice and ambiguity. Rituals might involve deliberate observation to collapse preferred outcomes, and symbolic acts of watching could become rites of decision and responsibility. At the same time, the cultural poetry must face rigorous scrutiny. Scientists on such a world would build metrology stations with noise budgets and test parades. Reproducibility would be the litmus test. A claimed landscape that behaves like an interference pattern must produce predictable fringes under controlled input light and must survive cross-checking that rules out ordinary atmospheric optics like thin film scattering, multiple reflection layering, or variable aerosol distributions. Instruments would measure coherence length, which is the scale over which phase stays correlated, and they would track decoherence times, which indicate how long a pattern survives. Teams would publish raw waveforms and blind data sets so poets and shamans cannot be the only witnesses to wonder. Controversy would be inevitable. Early explorers and artists will speak in ecstatic metaphors, and marketplaces will sell experiences that promise a private collapse. Late-night papers will publish uncontrolled observations. Careful physicists will answer with graphs and repeatable setups, and sometimes with sober corrections that turn a myth into a specialized refractive effect. Visual storytelling for such a realm is irresistible and instructive. Show scaled interference patterns sweeping over entire valleys like the ripples of a cosmic pond. Render artist concepts of shifting landscapes where a temple appears in one fold and evaporates in the next. Cut to laboratory scenes where scientists in quiet domes measure phase stability, calibrate laser-like probes, and argue over whether a signal is truly quantum or merely clever stacking of microstructures. Let an artist stand beneath a fringe and describe the feeling of being observed by light that refuses a single answer. Above all, carry a caution across the wonder. The language of waves and superposition makes a fine poem, but physics demands more than good metaphors. Distinguish between the thrill of a story and the hard proof that a fog carries coherent quantum states at scales where people can walk through them. That distinction is the difference between a living myth and a scientific revolution. A gas giant can hide a sky inside itself. Beneath the familiar bands and storms there could, in speculative theory, be a vast hollow region, a cavernous interior where gravity and pressure trade places, and where archipelago-like platforms drift like islands under an alien firmament. Some astrophysicists sketch natural routes to such hollows, others outline deliberate engineering scenarios, and both paths illuminate the same stubborn engineering truths about stability and maintenance. One natural pathway begins with resonant waves in a rotating, stratified atmosphere. Powerful standing waves can concentrate momentum and carve low-density pockets by redistributing mass into belts and walls, leaving a relative cavity of lighter gas or suspended aerosols. Over millions of years, those pockets could persist if the planet's rotation, internal heat flow, and compositional layering conspire to balance inward pull and outward pressure. The alternative is deliberate construction, where an advanced intelligence excavates, sculpts, or stabilizes an internal chamber by moving mass and by installing active supports. Both ideas face the same hard physics. A hollow region must fight collapse. The surrounding mass of the giant exerts relentless inward gravity, and pressure gradients want to smooth any discontinuity. Without continuous counterforces, a cavity slumps and fills, or the overlying layers sink and shear into turbulence. Stability requires either a steady outward pressure source or a structural mechanism that carries load across the void. How could such counterforces exist long enough for cities to live inside? One possibility is sustained internal heat. If a planet has a strong heat flux from a hot core, convective upwells and buoyant plumes can maintain lower density channels where gases rise fast enough to keep a pocket from collapsing for geological epochs. Those convective systems act like supports made of motion rather than metal, a fluid scaffolding that balances weight with ongoing circulation. Another possibility is magnetic and electric support. A giant with a deep conducting envelope can generate massive magnetic fields and currents. If fields are shaped and controlled, they can exert pressure on ionized gas, creating magneto-hydrodynamic cushions that push back against inward collapse. Think of a magnetic sheath that behaves like a flexible wall, guiding plasma flows and holding arches of charged material in place. Such supports demand enormous energy and precise control, so they feel more like the work of an engineering civilization than a natural accident. The interior environment would be strange and beautiful. Gravity inside a large cavity is not uniform in the way it is on a planet's surface. Near the inner surface, the effective gravity could be low, almost a whisper, because much of the planet's mass lies above you. In pockets where buoyant layers float, a human could walk with a tentative step, or a farmer could tend terraces where vines climb on hovering scaffolds. Floating cities would anchor to internal strata with tethers and dynamic winches, with each anchorage riding currents like a moored ship on a sea of air. Platforms might be built from lightweight frameworks and rigidized membranes, their undersides swept by ion drives or by controlled upwell jets to maintain altitude and orientation. Agriculture would abandon broad acre plows and adopt vertical and modular systems that exploit low gravity. Root mats could unfurl across suspended decks, aeroponic towers would hang like chandeliers, and algae farms would drift in translucent bladders collecting filtered light. Nutrient cycling would favor closed loops because resupply is slow and expensive. The interiors create novel navigation. Instead of roads, there are cloud canyons, corridors carved by wind shear and thermal gradients, lit by filtered glow from above and punctuated by waterfalls of condensate that fall from higher layers and evaporate before they touch a deck. Ships and personal skiffs do not fight constant gravity-bound drag. They trim fields and vector fans to catch buoyant currents and to surf the differences between layers. Pilots become intimately familiar with layers and eddies, reading them like sailors read tides and wind. The sensory life aboard such platforms would be unequaled. Dawn is not the rise of a star, but the shifting of a color band as a new convective layer arrives. Nights can be illuminated by internal aurora like curtains produced by charged flows slapping magnetic supports, and storms move along internal jetways with a slow theatricality, sweeping cities in curtains of vapor that smell of exotic chemistry. For a visual sequence, a creator can open with a cross-section that peels the giant like an onion, revealing a dark inner cavity rimmed by glowing cloud strata and dotted with floating islands. Fly-through shots can move from the busy promenade of a platform into a narrow cloud canyon where condensate falls in glistening threads, and close-ups can show tether nodes flexing as a city adjusts to a passing thermal plume. Schematics that overlay pressure gradients and magnetic field lines give the audience the sense that this beauty is precarious and engineered. Engineering questions are the heart of the mystery. Could humanity build such spaces or even retrofit an existing giant to carve a living hollow? The challenges are staggering. Every ton moved matters when dealing with a planetary scale mass. Creating magnetohydrodynamic supports requires not only materials that can survive intense currents and temperatures, but also an energy source large enough to feed them for centuries. Tapping internal heat flows or redirecting convective channels demands control over planetary scale fluid dynamics, the kind of mastery that changes a world. Cost is not only energy, the timeline is long. Natural resonant shaping trades time for subtlety, while engineered hollowing trades immense energy and technological reach for speed and precision. There is also a moral and ecological calculus. A gas giant is not an empty vessel. Its chemistry and field systems are ecosystems at a scale we barely understand. Altering them could erase native patterns that took eons to assemble. An alien intelligence might already live in those currents, or fragile probiotic chemistries might be forming in the hollowed air. The decision to enter and to alter a giant would be as much an ethical act as an engineering one. The final, unavoidable question hangs like a tether above the void. If a civilization had the will and the resources to fashion a hollowed giant into a habitable interior, what would they be willing to trade in exchange for the dream of a sky within a planet, and who gets to decide when the cost is that high? Eclipses become the heartbeat of whole worlds. In the timed eclipse system, 2 or 3 suns and their planets fall into a precise, repeating rhythm so that shadows return like clockwork and last for hours and even days. The trick is simple and elegant. Orbital periods lock into neat ratios so planets and stars line up at the same points again and again, and the orbits themselves wobble so little that the alignment keeps its timing for generations. Think of it like a set of gears whose teeth match perfectly. When the gears turn, the same tooth meets the same notch and the shadow sweeps across again. Long eclipses follow when relative motion across the sky is slow, when a planet moves almost sideways past the stellar disk, or when a distant companion star slides gently into place and lingers behind another for a long, slow descent. Low precession and shallow orbital tilt keep the path of the shadow stable, and that stability is what gives societies something they can plan their lives around. The climate answers to that clock. Days that lose sunlight for extended stretches cool in predictable waves. Surface temperatures drop and then creep back up after the light returns. Air circulations shift. Long cooling events can trap moisture and spawn dense fogs along the terminator. Light-dependent ecosystems evolve to the cadence. Plants build deep stores of sugars and starches and then release them in a single explosive growth when the sun returns. Microbial mats under stone time their respiration to eclipse hours. Nocturnal or shade lovers may find the long dark a bounty, while strict daylight hunters and pollinators must either shelter or migrate. Human culture bends around these rhythms. Farmers write planting schedules to the eclipse calendar, planting resilient seedlings that can sleep through a shadow and bloom the instant light returns. Whole crops are synced to the longest eclipses, so harvests come in waves tied not to weeks or months but to an astronomical beat. Religion and ritual follow the same path. Some communities hold week-long festival ceremonies at the heart of an eclipse, turning shadow into sacred pause. Others practice silent days where speech and work are taboo during the deepest dark. Architecture adapts. Greenhouses become vaults with layered thermal mass that hold warmth through long nights. Walls are thick and filled with phase change materials that absorb heat in the bright hours and release it slowly during the eclipse. Power systems are designed to store at scale. During full light, settlements push energy into pumped reservoirs, into compressed gas banks, and into chemical stores such as hydrogen produced from excess electricity. Massive flywheels spin through the bright spans and dump their stores into grids when the sun vanishes. In places with technological reach, fleets of orbital mirrors tilt in to keep chosen fields lit through the eclipse for critical crops, while other regions intentionally darken to preserve rituals and to let certain species complete their cycles. That split creates social choices: who controls the mirrors, who decides which districts get kept artificial day, and which must learn deeper endurance. The social texture becomes as important as the engineering. Visuals for this world are naturally dramatic. A choreographed animation can sweep across a planet as 2 or 3 stellar disks slide into a slow, layered eclipse, casting long moving bands of twilight that roll over cities and seas. Close-ups of calendars carved into stone and into glass show generations of marks that track the precise beats, as if every home keeps the stars on its wall. Reenacted rituals place people under the shadow with slow ceremonial movement, lanterns raised in patterns that echo the astronomical geometry. Cutaways show farms sealed under domes, thermal storages grinding away, and orbital mirror arrays tilting like a field of silver leaves to hold a chosen valley in borrowed sun. The precision itself invites invention. If eclipses come with clockwork regularity, engineers can time the most demanding operations to those predictable windows. Launch sequences could ride the sudden calm of a long dark when thermal gradients drop and winds slacken. Massive construction projects could use the cool hours to harden materials that otherwise would warp in constant glare. Synchronized melts and freezes could be used to sculpt continental features or to pump heat across a planet in carefully timed cycles. Could a civilization learn to orchestrate its greatest works by arranging who stands in light and who stands in shadow? Not all belts are dead rock. Some could be gardens of light, a ring of asteroids stitched together by living glow that spills into the night for whole worlds to see. Imagine fine films of organisms clinging in sheltered pores, slow bioluminescent mats coating the lee sides of boulders, and tiny colonies nested inside pockets of ice that melt and refreeze on long seasons, each organism a tiny lamp fed by chemistry rather than sunlight. The idea sits on simple building blocks we already know about on Earth and in space. Extremophile microbes endure heat, cold, radiation, and vacuum by hiding in cracks, by slowing metabolism, by making protective biopolymers, and by riding out damage in dormant states. Tardigrade-like durability and microbes that live inside rocks teach us that life can resist far more than we once believed. Bioluminescence itself is a repeatable trick of chemistry. A molecule that releases light when it oxidizes can work with surprisingly little energy if the pathway is tuned to slow, steady consumption. On an asteroid, that energy can come from several sources. Radiolysis of ice by radioactive elements can free reactive compounds. Solar wind-charged particles can create surface chemistry and then trigger reactions when materials are warmed. Friction from micrometeorite impacts and tidal flexing can liberate trapped volatiles and spark short-lived blooms of light. Engineers and evolutionary tinkers could also design organisms to run on those low fluxes, to convert trace chemical gradients into faint, steady glow, or to flare in spectacular pulses when warmed by a passing comet or by sunlight during a close approach. The result could be a belt that looks alive from orbit and that writes a slow, living skyline across every night. That possibility unspools a dozen human stories. Seed banks and engineered microbes are already proposed as tools for terraforming and for creating biosignatures we can see from afar. A luminous belt could be the cosmic equivalent of a lighthouse, a navigational aid, and a statement that life has reached outward. It could also be a tourism industry on a planetary scale, with orbiting promenades and glass domes where people watch the slow drift of luminous trails and book holidays to stand beneath a ring that glows like a second galaxy. The engineering is seductive because the infrastructure is lightweight. A few strains seeded into tens of thousands of sheltered niches could amplify into a visible spectacle over decades rather than millennia. But the romance collides with ethics. If the glow is seeded by us, we alter a system that might otherwise develop its own paths. If it is allowed to develop naturally, we might miss the chance to make it bloom sooner for people who need resources or for cultures that crave wonder. There is the question of contamination as well. Introducing engineered life could obscure the scientific record and erase precious clues about abiogenesis and natural chemistry. It could also irreversibly change local chemistry and resource availability in ways we do not foresee. Visual storytelling on this topic is immediate and cinematic. Sweeping concept art can show a belt like a crown of fireflies turning slowly against the stars. Close microscope-style shots can reveal filamentous microbes exuding bioluminescent gels and tiny colonies pulsing in waves when a micrometeorite impact wakes them. Documentary-style interviews can frame the debate with soft-spoken exobiologists who talk about stewardship and with entrepreneurs who speak of visitor pavilions and new economies that light up the night. Time-lapse sequences could show a dull belt brighten over years as a seeded ring spreads its glow, and side-by-side graphics could contrast the scientific value of leaving a system pristine with the cultural value of sharing a living light for all to see. The luminous garden belt asks an old question in a new key. Who has the right to plant living lights across the heavens, and what responsibilities follow once those lights take on lives of their own? The sky here never brightens, yet the world hums with power. A star with a strange magnetic personality bends its field lines like an invisible loom, and those bent threads reach out to the planet and stitch together a steady stream of charged particles. Think of a giant magnetic thread connecting star and world, a flux tube that guides particles the way a river channel guides water. Where that tube meets the planet, its magnetosphere becomes a living dynamo, a steady flow of electrons and ions that can be harvested like wind or current. On this planet, light is incidental. The true daylight is the slow, faithful tug of magnetism and the heat born from inside the crust. The physics is familiar in a new voice. Planets that sit inside complex stellar magnetic topologies get hit in predictable places by charged particle streams, much like how Jupiter's moon Io sparks a glowing bridge along Jupiter's field. Those impacts do not just make pretty auroras, they inject energy into the upper atmosphere, they spin currents through the magnetosphere, and they seed the crust with charged chemistry that fuels reactions on the surface and below. Over geological time, life can learn to use that steady electron rain the way coastal ecosystems learn to use tidal energy. Microbial mats grow conductive filaments to harvest electrons. Plants evolve root tips that double as electrodes, drawing charge from mineral veins like a battery. Entire food webs base their metabolism on redox reactions powered by magnetospheric input rather than on photosynthesis alone. Cities respond as engineers would and as poets would admire. The skyline becomes a forest of harvest pylons and tethered coils that reach up like fingers into the magnetic wind. Those structures are not tall like towers that chase sunlight. They are wide and curved to maximize field coupling, each wrapped with loops of superconducting cable and with arrays of charged collectors that channel current into the ground. Streets lead to communal intake halls where the raw flow is tempered, rectified, and parceled into neighborhoods. Basements are no longer a place for storage and silence. They are the primary living rooms of power, cavernous hubs where dynamos spin in steady, low hum and where citizens meet, trade energy credits and exchange warmth. On cold evenings, people gather in heat galleries that glow with the soft blue of plasma panels powered directly by magnetospheric harvests. Domestic life rewrites itself around flux and field. Appliances are built like small harvesters rather than like passive loads. Refrigeration units draw small eddy currents from local coils and lock them in chemical stores for off hours. Streetlights are not illuminated by wires that bring distant photons, but by neighborhood loops that siphon a trickle of current from the ambient field and feed electroluminescent membranes. Gardens move into the deep, into terraces lit by low-voltage arcs that encourage fungi and engineered phototrophs to thrive in permanent dusk. Even clothing becomes conductive. Fabrics carry microfilaments that harvest slight field gradients and translate them into warmth or into faint light that ripples when the magnetospheric flow pulses. Architecture adapts with a warmth that feels domestic and slightly other. Facades face magnetic poles rather than facing suns. Windows are small and deeply shaded because the glare of magnetospheric auroras is a faint thing and because thermal management comes from within. People build with layered rock and conductive sheathing so that a building S-frame doubles as a current conduit and as a heat sink. Public plazas are often subterranean amphitheaters where ambient hums are tuned into music by big resonant coils. Concerts here literally play with the planet's currents, growing swell and silence by nudging the local field with a controlled coil at the center of the hall. Visually, the system is distinctive and cinematic. Diagrams that show the star's twisted field lines meeting the planet bring the concept into plain sight, with color-coded tubes that end at the magnetospheric intake points and arrows that show the electron tide flowing inward. Subterranean city renders should feel intimate and warm, broad caverns lit by ribbon-like banks of electroluminescent panels and by slow steam vents where geothermal heat meets magnetically driven power plants. Close-ups of speculative appliances make the idea tactile. A kitchen hob is a compact magnetic induction array that draws from a local field node. A window-sized panel is a passive radiator that converts magnetic fluctuations into soft glow. A domestic heater is a sealed cavity where conductive salts absorb current and release warmth on demand. Show hands reaching out to touch a coil and feeling a faint, steady vibration, and show children learning to read local hum signatures like weather maps. The biology and industry interleave. Bioprospectors seek microbes that convert charged particle flows into useful compounds. Farms grow electrofungal nets that masticate mineral dust and excrete sugars and structural proteins. Mining becomes intimate with circuitry. Shallow boreholes tap conductive seams that are charged by magnetospheric deposition, and those seams power small foundries that sinter metal with almost no external fuel. Transport favors enclosed, low-drag tunnels and magnetic sledways that piggyback on ambient currents. Long-distance ships still need fusion, and fusion remains for travel. But everyday life runs on the slow, gracious generosity of a star that chooses to whisper rather than flood. Aesthetics follow function and then invent new delights. Permanent dusk creates a palette of muted blues, greens, and incandescent purples. Artists trade in fields and in motion rather than in stark light and shadow. Sculptors shape ferrofluid gardens that bloom in ordered patterns when field generators pulse beneath them. Painters work with magnetic ink particles that reorganize under a hand-held coil, so a painting never stays fully the same, and a gallery visit is a unique dialogue between viewer and field. Musicians compose pieces that sync with predictable magnetospheric beats, layering tones that rise when a particle stream swells and that fall when the flux eases. Performance art becomes relational because the audience literally alters the electricity of the room by moving their conductive garments. There are ethical and practical debates embedded in this life. Who controls the harvest nodes? How is access to the steady, slow sun shared? Plutocrats might hoard the best intake shores on cliff faces and sell light by subscription. Communitarian councils argue for distributed micro-harvesters and for legally guaranteed neighborhood basements that deliver baseline power free to all. The environment itself asks for care. Magnetospheric flows can change chemistry on a scale of decades, concentrating nitrates or metals in shallow soils and altering river chemistry. Stewardship requires a blend of geophysics and empathy because rewiring a planet's electron economy changes food webs as surely as damming a river changes floodplains. If you were an artist raised under that distant hush, how would you work when magnetism is your primary sun? Would your canvases breathe when a current passes through? Would your choruses translate particle rain into rhythm? Would lovers write letters that shimmer only when held near a coil and fade in the dark? How would a museum display an auroral dawn that never comes from above but always arrives from the ground and from the hum beneath your feet? A star that eats its own colors. Spectroscopists first noticed it like a barcode losing bars. For minutes, hours, or sometimes days, a narrow band of the star's light would simply fade from the spectrum and then come back as if someone had erased a single hue from the stellar song. Telescopes recorded clean spectra with familiar absorption lines, and then those lines thinned and vanished only to reappear with no warning and no obvious change in the star's overall brightness. The data are precise and strange. Time series spectroscopy shows transient absorption lines that trace a disappearing color and return like a tide. Photometry sometimes hints at small dips in matching bands, but not always, so the effect is not merely dimming. Polarimetry and multi-wavelength checks rule out many instrumental errors because independent observatories on separate continents see the same vanishings in near-perfect sync. There are three broad families of explanations, and each feels like a story with different stakes. The simplest is drifting dust. A cloud of particles passing between us and the star can pick off certain wavelengths depending on the particle sizes and chemistry. Fine particles tend to scatter short wavelengths more and leave reds, while larger metal-rich grains can absorb narrow bands where their molecules resonate. If a disk fragment or cometary cloud wanders through the line of sight and carries a strange mineral mix, the spectrum can wear holes for a while. Those clouds would likely radiate heat in the infrared, so telescopes tuned there can catch a warm fingerprint and map the dust's motion. The signature of dust is messy and changing, and it usually shows a smooth wavelength slope and polarization signatures that betray scattering. A second explanation sounds less natural and more deliberate. Imagine filters engineered to remove particular bands like a cosmic equalizer. An opaque screen or a lattice of orbital shades could block a narrow slice of the spectrum without knocking out everything else. If an intelligence were trying to hide specific emission lines that betray industrial activity or a biochemical marker, a targeted filter would be a subtle way to do it. Engineered filters would likely repeat with orbital cadence and show geometric traits. They might cause precise, step-like cutoffs in the spectrum rather than the smooth curves of natural dust. Detecting such regularity and geometric repeatability would push the conversation from astrophysics toward archaeology of intelligence. A third possibility opens a door into new physics. In extreme plasmas and exotic atomic conditions, familiar absorption features can shift, broaden, and even vanish as atoms rearrange themselves under pressure, magnetic stress, or unusual ionization states. Unknown molecules or transient excited states could selectively soak up or reroute light in ways our current lab catalogs do not predict. Laboratory plasma chambers and laser spectroscopy are already being used to chase this idea. Scientists recreate dense ionized gas and point calibrated lamps through it to test whether known lines can be suppressed by temperature, density, or electromagnetic fields. If a terrestrial plasma can erase a spectral line under controlled conditions, we get a model to compare with the star's behavior. Astronomers track these vanishings like weather. Observatories run high-cadence monitoring programs that take spectra every few minutes and then stitch those snapshots into a living movie of change. Space-based instruments fill in atmospheric gaps while ground telescopes provide redundancy and polarization data. Teams cross-correlate spectra from many sites to rule out instrument quirks and to triangulate whether the effect appears across the star's whole face or only from one limb. Radio and infrared observatories listen for correlated signals. Citizen science arrays and small aperture telescopes join the network because a single event can move from curiosity to discovery in a matter of hours. The result is a web of watchers that can pin down timing, repeatability, and angular extent. The consequences of specific bands vanishing ripple beyond astrophysics and into life and industry. Photosynthesis depends on particular bands of light. On Earth, plants favor red and blue bands because those photons drive the chemical reactions that build sugars. If a distant sun periodically loses the red band, a planet's surface flora would struggle. Life could adapt by evolving new pigments tuned to the surviving wavelengths or by shifting growth into caves and beneath reflective canopies that concentrate the remaining light. Human settlers would change their agriculture. Farms would run tuned growth lights that replace missing bands, and greenhouses would filter and remix stellar light like a kitchen, balancing what the plants need and what the star currently offers. Color perception and culture would change too. Human vision reads color from 3 bands, and losing a band warps how everything looks. Art, fashion, and design would all shift. Industries that rely on precise bands such as semiconductor lithography, photochemical manufacturing, and remote sensing would feel the pinch. A vanished ultraviolet band can ruin a manufacturing step that depends on a narrow photon energy to pattern a surface. Satellite-based mineral surveys that identify ores by their spectral fingerprints would lose diagnostic markers and need new algorithms. Economies would adapt or move processing to orbit or to other systems where the light remains whole. For visuals, a creator can make the mystery visible. Show animated spectral graphs that trace a line as it hollows out and then fills again with a slow, haunting motion. Cut to telescope footage where filters highlight the missing band, and to lab scenes where researchers try to reproduce the effect with glowing plasma tubes, tuned lasers, and dust-scattering chambers. Show a greenhouse where lights flick on to substitute for absent bands, and then a color palette sequence where paintings and fabrics shift to match the new sky. Close-ups of spectral plots with overlaid timing maps make the phenomenon feel measured and real. The debate that will not leave the room asks a blunt question. Is this a cloud of strange mineral dust telling a natural tale, or is it a deliberate veil built by hands that do not belong to the star? To tell the difference, scientists look for thermal echoes that dust must emit, for polarization signatures of scattering, and for the fine molecular fingerprints that only chemistry can make. They also search for clockwork. An engineered filter will often repeat with flawless cadence or present geometric transits that betray structure when mapped across the stellar disk. A natural cloud is messy and unpredictable and will usually leave an infrared glow or a trail that telescopes can image. But what if the veil is both clever and cold and leaves almost no heat signature? Then the only clues may be the pattern of disappearance across many lines and the presence of unnatural regularity in timing and shape. When the next vanish comes, will we be able to read it as weather or as a whisper aimed in our direction? One comet kept steering itself. Astronomers tracking it noticed small but persistent nudges that did not match gravity alone, and that could not be fully explained by simple sublimation as it warmed. The first clue comes from precise position measurements taken night after night. When a comet appears where your gravity models predict it will not be where you expect, that mismatch is a red flag. Astrometry shows the path, photometry tracks brightness and coma changes, spectroscopy reads the composition of jets. When those datasets are layered together with careful timing, the picture grows clearer or stranger depending on the evidence. Non-gravitational accelerations are a familiar tool in the observer's belt. Comets vent gas and dust when sunlight warms volatile pockets, and those jets act like tiny rocket engines pushing the nucleus. We model that effect, and usually it lines up with the star-to-comet distance and with seasonal heating of the surface. The unusual case is when the thrust pattern seems targeted, or when course corrections occur at times when simple thermal models predict nothing. That is where the word signaling slips into casual conversation. Detecting deliberate change is a problem of exclusion and of pattern. Analysts compare the measured acceleration against what a passive model would allow. They map coma structure and jet orientations. They look for repeatable sequences rather than one-off flares. They ask whether the energy budget makes sense. Could the comet expel enough mass to account for the observed speed change without ripping itself apart? If not, the mechanical explanation stretches. They also check for spinning torques. A rotating nucleus with asymmetric jets can wobble and alter its orbit in complex ways, and that can look startlingly clever until you reconstruct the surface geometry and see it driven by shadows and composition patches rather than by choice. The possible causes fall into three broad categories. The first is fully natural structure. Pockets of volatile material under a crust can ignite in directed bursts as sunlight finds a fresh fissure. Seasonal changes in rotation or in orientation can concentrate venting into jets that act like thrusters at predictable points in the orbit. The second is engineered mechanism. Tiny propulsion units or mass ejectors hidden in a nucleus could produce controlled thrust and course corrections. In that case, an object that looks comet-like could be a probe, an automated ship, or an artifact with a mission and with reaction control systems scaled to its mass. The third and most provocative is the possibility of biological agency. Microbial communities that live within pores could adjust metabolic rates to control gas release. A larger organism sheltering beneath a frozen crust might expel material to move or to communicate. None of these explanations are easy to accept without proof, and each demands evidence the other two do not share. That is why humility matters. Humans are expert storytellers. We weave agency into pattern because agency makes sense of irregularity, but pattern does not always equal intention. Jumping from detection to declaration risks anthropomorphism and the weight of our own narrative wants. Scientists therefore frame their claims carefully and test hypotheses that remove human bias. They simulate random thermal bursts, run Monte Carlo orbit fits, and search for signals that are statistically unlikely to arise from noise or from known physics. The cultural fallout of a comet that registers as more than rock is immediate and deep. Philosophers and ethicists ask whether agency requires nervous systems or whether coordinated material processes count as minds on a spectrum. If a small body can steer itself deliberately, that forces a rethink of where life and agency begin. Is a sentient system defined by metabolism and replication, or by the capacity to change its environment in goal-directed ways? Those questions are not just academic, they shape policy. Space law and planetary protection frameworks must decide whether to treat a possibly sentient object as protected heritage or as permissible resource. Proposals on the table range from a strict moratorium on active contact until independent verification to a tiered approach where passive observation and low-risk listening are allowed, while any attempt to send a probe or to harvest material requires international clearance. Some suggest a digital do-no-disturb register for objects that show non-random behavior, a temporary protected status that buys time for scientists and ethicists to convene. Others urge more radical steps, Indigenous thinkers and cultural custodians remind us that the moral stance we take will echo across centuries and across species. They argue for humility and insist that we err on the side of non-intervention when uncertainty is high. Practical rules are emerging in draft form. Any mission that plans to approach a suspicious comet should publish an open intent, allow international inspection of telemetry plans, and prefer non-invasive sampling like high-orbit spectroscopy or laser altimetry over physical contact. A strict chain of custody for data and materials is advocated so that if biological signatures are found, the response is measured and not driven by market pressure or national competition. The human conversations are already as vivid as the data. Artists compose speculative messages and ethicists gather to debate consent for objects that cannot speak in human tongues. Engineers sketch benign envelopes and soft touches that would cradle a nucleus rather than drill it. Creators can help viewers feel the complexity with visuals that combine time-lapse overlays of trajectory corrections with simulated coma jets firing in slow motion, and with interviews that show ethicists and planetary scientists hashing out what consent might mean for a wandering rock. Close-ups of models that quantify the thrust versus the expelled mass make the physics clear, and the questions remain sharp and unsettling. If an object moves with purpose, do we try to reply and risk altering a mind we barely comprehend? Or do we hold ourselves back and become listeners in a universe that may already be speaking in its own low, cometary voice? Would you try to speak to a wandering rock that might already hear? A cold star can flare like a frozen torch and change a landscape in an hour. These are not ordinary solar tantrums. In the frozen flame star, the surface temperature of the star sits low and steady most of the time, but its magnetic field stores enormous stress until it snaps. When those twisted lines reconnect, they release bursts of high-energy light and particles that hit nearby planets as a sudden, scorching pulse. The effect feels paradoxical, like a winter that briefly remembers summer and burns everything in sight before the cold returns. For a planet, the result is rapid bake followed by a refreeze, a geological heartbeat that melts and rehardens rock, boils shallow seas, and then leaves a glazed, glass-like crust in the wake. What could make a cold star behave this way? One route is an unusually strong fossil magnetic field trapped from the star's youth, tangled by differential rotation between outer and inner layers. Over long timescales, the field knots and knots again, and the only escape is a violent reconnection event. Another route involves close companions. A dense companion such as a brown dwarf or a massive planet can torque the star, stirring its outer layers and feeding magnetic shear. Streams of charged particles from an accretion remnant or from a thin surrounding disk can amplify currents until a single snapping event lets stored energy pour out. The physics is extreme but familiar in concept. Magnetic reconnection is the same process that drives our sun's flares, and it works by converting ordered magnetic energy into heat, fast particles, and intense light. Only here the storage and geometry are stranger, and the release can be far more concentrated at particular orbital phases. How violent are these frozen flames compared with a planet's own stability? A single burst can deliver enough thermal energy to melt the top layer of crust across a hemisphere down to depths of tens of meters. It can vaporize shallow lakes and bake soils into welded glass. Those are meaningful fractions of what a planet holds at its surface, but they remain far below the gravitational binding energy that keeps a planet whole. In other words, the star's flare reshapes the skin without ripping the body apart. That makes the frozen flame a machine of renewal rather than wholesale destruction. Repeated cycles can rewrite geology on human timescales, turning landscapes into layered palimpsests where each flare lays a new glass skin, and each refreeze traps fossils and artifacts like snapshots. Survival on a world like that forces invention and ritual in equal measure. Early warning systems become the first line of defense. Astronomers and sky watchers monitor subtle precursors in radio and ultraviolet bands, and communities treat those alerts as weather advisories for planetary fire. Rapid response shelters are an art form. They are not merely bunkers but quick-folding skins. Imagine panels that unfurl from compact rolls and deploy as reflective domes in minutes, layers of high reflectivity that bounce back much of the incoming pulse. Behind those outer shells, a second layer of thermal mass absorbs residual heat and stores it without transmitting it to living spaces. Phase change materials act like thermal sponge, melting and solidifying to buffer temperature swings. Underground caverns with deep shafts and thermal chimneys give people a place to ride out the peak while geothermal vents balance pressure and humidity. Materials engineering goes beyond blunt insulation. Builders favor flexible architectures that can flex through cycles of expansion and contraction without cracking. Laminated ceramics with interleaved metallic meshes take the shock of sudden thermal gradients and distribute the stress. Shape memory alloys and elastomers that change shape when heated help components relieve stress without breaking. Microstructured coatings scatter and redirect high-energy particles before they hit critical layers. For infrastructure that must survive direct flare strikes, designs use layered redundancy, with sacrificial outer skins that vaporize and slough off while inner shells remain intact, and with distributed systems so a single strike cannot cripple a settlement's entire water and power supply. Human cultures adapt in stories and festivals as much as in engineering. Where harsh cycles reign, rebirth becomes the core myth. Communities sing the story of the day the rock bled glass, and each refreeze is a sacrament of renewal. Builders teach children to read the pattern of crust layers like family trees. Artisans collect vitrified shards cast by the last flare and use them in mosaics and public altars, literal slices of their planet's recent past. Some groups practice public repairs as communal ritual, sealing cracks together in celebrations that reaffirm cooperation after a season of furious change. Legends grow about ancestors who mapped safe hollows and about engineers who learned to speak to the star by timing mirror arrays to calm its moods. Those narratives carry practical knowledge in a form that is easy to pass across generations. Visuals for a creator are both stark and cinematic. Thermal imaging that sweeps across an impact zone reveals a searing pulse that blooms and dies, leaving a ring of slowly cooling crust. Engineers' mock-ups of flexible habitats show panels unfolding into reflective bells and then locking into insulated cores. Dramatized survivor accounts bring the human scale. A farmer describes watching a lake hiss and fuse at the surface, and the quiet day after when glass planes glowed like a harvested eye. A child plays with a polished shard, tracing the bubbles and fossils frozen inside, and the camera lingers on the small thumbprint of humanity in a newly minted landscape. There is a deep ethical and political question woven into the fire. Would a civilization living beneath such a star treat each flare as an oracle to be worshipped, composing ritual behaviors that honor destruction and rebuild in its shadow? Or would engineers aim to harness the pulses, timing power grids to capture the sudden flux and turning the temporary fury into a deterministic resource that fuels industry and settlement? Is reverence and art the safer path to long-term survival, or does the promise of harvest and control inevitably lead to attempts to shape or even to stabilize the star's moods? Which feels more likely if the choice is between kneeling before a frozen flame that reorders your world and building machines that try to bend the flame to human purpose? Night here is a chorus of reflected light. On Hespera, dozens of small moons wheel through the sky, and each one returns sunlight with its own voice, so the night is never flat and never the same. Small, bright ice moons flash like distant lanterns. Dark, iron-rich moons throw a warm, rust-colored glow. Tiny pocked stones scatter faint blue like pinprick sapphires. As they move, their phases shift and overlap, and the combined effect is a layered, echoing nightscape that changes mood hour by hour. One minute a neighborhood basks in soft silver wash from a near full moon. The next minute a band of darker satellites slips in and paints the same street with sepia shadow. Those overlays climb and fade like sound, so the sky feels less like a single lamp and more like an orchestra where shape, color, and timing score human rhythm. The reason the sky behaves this way lies in orbital choreography. Many of Hespera's moons fall into resonance patterns, which means their orbital periods lock into simple ratios and they tug on each other in steady beats. When neighbors fall into a 2-to-1 rhythm or into more complex chains, their positions repeat in familiar alignments. That repetition gives residents a kind of celestial metronome. Unlike a system with a single large moon where the phases follow a single cycle, the resonant web of dozens creates composite patterns. Full faces line up sometimes in cascading sequences, and sometimes eclipses of one moon by another throw transient dark slashes across the layered glow. Add differences in surface reflectivity and the palette multiplies. A high albedo moon covered in ice reflects a cool white, while a low albedo moon rich in oxidized metals returns warm tones. Some moons are covered in thin frost that glows green in particular starlight. Others carry basaltic dust that absorbs and redistributes a narrow band of light. The interplay of phase geometry and surface chemistry means the night is a dynamic painting whose brush strokes are orbital mechanics. Those changing skies bend the way life organizes itself. The simplest shift is timekeeping. Lunar calendars on Hespera are not a single line but a braided ledger. Months are measured by the recurrence of specific layered alignments, not merely by when one moon is full. Civic events use complex calendars that note which moons will be dominant in the evening and which will be in shadow. Farmers plant and harvest by layered light windows because some crops respond to the exact balance of cool and warm moonlight rather than to the total brightness. For artists, the sky is an instrument. Painters and textile makers design palettes that only resolve under a given moon chorus, and composers write music that mirrors the cadence of overlapping phases. Ensembles perform pieces where percussion mimics the quick flicker of small rock moons and strings swell with the long wash of larger satellites. Street performers tune their movement to the coming and going of particular gleams, and entire districts specialize in art forms that only make sense when layered moonlight is taken as the medium. Navigation becomes a living craft. On Hespera, sailors and pilots do not only read stars, they read moon layers like a layered map. Coastal pilots time departures to the appearance of a bright band that eases glare on certain channels, and caravan leaders steer by matching the pattern of shadows along ridge lines to recorded charts. Small differences in phase timing act like local landmarks. An outcrop that disappears beneath the shadow of a passing moon becomes a transient harbor marker, and radio beacons are often synced to particular lunar echoes so that an approach can be visually verified against an expected overlay. Even urban design borrows the sky as a guide. Streets are laid out along vectors that catch particular moonlight sequences for safety and for beauty, and plazas are oriented so that certain altars will be lit by the same moon every cycle. The way people build and live also shifts toward the layered light. Architecture on Hespera favors adaptive shutters and reflective canopies that harvest a chosen mix of bands rather than trying to reject all moonlight. Homes wear adjustable facades that let a household pick the character of the night within private rooms, opening to a silver veil for communal dinners and closing to amber dusk for sleep. Public spaces are designed as theatrical stages for the sky. Amphitheaters orient to take advantage of a cascade of small moons that line up for an hour each week and throw a moving chiaroscuro across a performance. Markets time their busiest hours to those windows when the moons align to make colors pop, and traders can spot goods clearly without artificial light. For navigation and safety, the most elaborate constructions are the lunar lighthouses, towers fitted with mirrors and phase-sensitive filters that amplify chosen moons to create long-range cues detectable from orbit. Visuals for storytelling are built for mood and motion. Time-lapse sequences that compress an evening into seconds can make the layered echoes feel like waves passing through a city, with light folding and unfolding in complex patterns. Diagrams that overlay moon orbits and show phase overlaps help viewers see the geometry behind the beauty. Close cultural scenes bring the human side into focus. A midnight market lit in shifting layers where fabrics flash different patterns as a dark moon slides past, and a musician conducting an ensemble whose tempo rises with the waxing of a particular satellite. Slow cross fades between a street painted in bluish ice moonlight and the same street warmed by a metallic orb, convey how the same place can hold different moods within a single night. There are small tensions too. Public festivals tuned to the moon chorus require coordination because a single misaligned band can change the effect. Some neighborhoods compete for the best lunar moments and negotiate shared windows for major celebrations. Traditionalists argue for rituals that honor the predictable cadence of resonances, while innovators use timed reflector arrays to sculpt new echoes on demand. That debate is part of the culture and part of the craft of living with a sky that keeps rewriting itself. Finally, imagine an open plaza on a warm Hesperian night. Thousands gather as a rising chain of moons steps through its phases one by one. Musicians cue the increasing brightness, dancers move into shadows and back into light, and mirrors on long poles flash coordinated glints that answer the echoing moons. The air is full of layered music and light, and the sky itself seems to join the chorus. Would you attend an outdoor festival choreographed to moon echoes? Some forests conduct electricity like living power stations. On a terrestrial world we will call the metallic forest system. Arboreal forms are not wood and leaf but towers of metal and crystal, spires that rise like trees and braid themselves into a canopy that looks at once botanical and circuitous. Up close the trunks are layered with lattices of conductive mineral, bark that rings when the wind passes and that channels charge the way a river channels water. At the canopy, the branches interconnect into webbed plates that catch charged particles from the stellar wind, and that guide lightning into controlled pathways rather than letting it strike at random. The effect is a landscape that hums with steady current and occasional thunderous pulses, a place where the sky writes electricity into the land. How could such things form? One hypothesis starts with electrochemical precipitation in an active, charged atmosphere. If the air carries a steady flux of ions and if mineral-rich aerosols rain down, tiny conductive seeds can nucleate and grow in electric fields. Over long spans, electrochemical deposition favors branched dendritic patterns that follow field lines, producing tree-like columns that build by accreting metal and mineral from the mist. Another route is simple high metallicity in the mantle and crust. Planets born in metal-rich regions of a protoplanetary disk may cool with large veins of native metal and sulfide networks near the surface. When fluid flows or vapor escape concentrate along fractures, mineral growth can fossilize into arborescent forms as lava and hydrothermal flows cool into filigree. A terrestrial analog helps make the idea less alien. On Earth, we find mineral dendrites on rock faces and metallic filigrees in deposit veins. We see chemical gardens in laboratory tanks where salts and alkaline solutions build plant-like chimneys, and we observe manganese and copper dendrites in mine waters that look like tiny metallic trees. Those patterns are small and fragile on Earth but scale up plausibly on a world where chemistry, gravity, and long-term field stability cooperate. What would human use of such a forest look like? First and most obvious is electrical harvesting. The spires are natural conductors that can intercept a steady stream of charged particles from a wind that would otherwise sail past empty atmosphere. Engineers could anchor collectors along trunk surfaces and tap currents measured in tens to hundreds of amperes per square meter across active plates during calm conditions. And during electrical storms, individual trunks could channel short bursts that peak in the order of tens of thousands of amperes in a single lightning stroke. Converted and conditioned, those flows translate into energy yields on familiar scales. A single well-sited trunk with broad canopy coupling might produce 1 to 10 megawatts continuously in a high current zone and spike to hundreds of megawatts during an intense storm if captured safely. Arrays of trunks then form distributed power grids that are less vulnerable to single-point failure than centralized farms. Those numbers are rough sketches, but they give a sense that a living forest of metal could power cities without acres of panels. The metallic trunks also offer structural and ecological niches for vertical farming. Imagine terraces wound like rings around a polished rib where irrigation runs through capillary channels embedded in the metal. Conductive trunks supply low-voltage power and localized microclimates for hydroponic bays, and photonic coatings on branch plates can tune which bands of starlight reach leaves or algae panels. Farms could live in the shadowed grooves while solar harvesting continues on the exposed ribs. In such a design, food production hugs energy production, folding two vital needs into the same vertical spine. There are efficiencies and hazards entangled in that intimacy. The great danger is conductive storms. The same properties that let trunks collect steady current make them effective lightning channels, and when multiple spires braid into a single canopy, whole regions can be subject to coordinated strikes. Those strikes can induce surge currents across miles and can fry naive electronics if shielding and dissipation are not robust. Settlements woven into trunks would need layered grounding systems, sacrificial fusible links, and capacitive buffers that smooth impulsive loads into steady stores. Magnetic coils and superconducting catenaries could route currents into safe banks, but they are complex and expensive. Human presence also invites corrosion and fatigue. Metal living forms exposed to charged flows and to varying thermal cycles develop stress fractures and surface migration of ions that change conductivity over decades and centuries. Maintenance becomes an industry and a cultural practice. Repair crews climb like arborists fitted with magnetic grapnels and robotic patches. An entire profession center on reading the hum of a trunk to predict where a tier will open next. More philosophically, the line between living and not living blurs. Some trunks actively regulate current by opening and closing ionic valves formed from mineral membranes, reacting to prolonged storms by rerouting flows to avoid burnout. Others show slow cycles where growth appears to follow resource gradients, adding filigree where current is richest and withdrawing where it is poor. If a structure changes its environment, repairs itself, and directs flows purposefully, does it qualify as organism, or does it remain a geological formation with peculiar behavior? The question is not purely semantic. If metallic forests are alive in any meaningful sense, then intervention carries responsibility. Harvesting their currents might be akin to milking rather than mining, requiring consent and stewardship rather than extraction. If they are geological, their exploitation reads as resource development and must be regulated accordingly. Visuals for a creator make these distinctions tactile. Macro shots of metallic bark gleaming with fine crystalline texture sell the sense of alien wood, while tight close-ups of a branch's cross-section reveal circuit-like veins and filaments that glow faintly as charge pulses through. Aerial footage that drifts over a canopy shows a network that looks like a printed circuit board scaled to continental size, plates intersecting like soldered joints and light traveling along traces in patterns that look designed. Scenes of settlements woven into enormous trunks underscore human scale, platforms bolted into grooves, elevators sliding in magnetic rails, gardens blooming in sheltered rings, and maintenance crews dangling beneath overhangs to replace a corroded splice. An artful cut from a lightning strike arcing across the canopy to the gentle hum of a market powered by a trunk brings the wonder and the risk into one frame. The thought that lingers is plain and unavoidable. Would we call those metallic trees organisms worthy of respect, or would we treat them as geology to be mined and engineered for gain? Which choice would you make if the forest itself seemed to answer back to the currents it channels? Some dust keeps secrets for millennia. Astronomers found a ring of cold particles circling a lonely star and then noticed strange patterns hidden in the spectra and in the polarization of scattered light. At first, the patterns looked like noise with an elegant twist, repeating beats and narrow band gaps that some analysts mapped into sequences that resembled mathematical progressions and prime counts. A few groups published tentative decodings that read like an archive more than a greeting, a fossil record compressed into dust and etched across orbital lanes for a future observer to read. The image of a star that carries memory in its rings is seductive and almost cinematic, but the real work begins the moment fascination meets method. Scientific caution is not cynicism. It is a set of tests and an insistence on reproducibility. Pattern detection is easy in a human brain and hard in data. The mind sees faces in clouds and numbers in noise, which is why analysts demand statistical rigor. Signals must survive blind reprocessing, simulated noise trials, and checks that rule out instrument quirks and software artifacts. Teams run randomized controls and compare the candidate pattern against ensembles of synthetic rings produced by natural processes to see whether the apparent order could arise by chance. Beyond statistical tests, there are many natural ways that dust can organize into what looks like signal. Tiny moonlets shepherd particles into repeating clumps, magnetic fields align grains into polarized bands, and plasma instabilities can write quasi-regular ripples across a ring. Chemical sorting can concentrate isotopes and minerals along orbital lanes, producing spectral lines that vary with position and viewing angle. Even collisional cascades can produce periodicities that mimic intentional encoding. Each plausible natural mechanism must be modeled, observed, and falsified before any claim can stand. The stakes reach far beyond telescopes. If what we are seeing truly is an interstellar archive left by a prior intelligence, the cultural and philosophical shocks would be immense. Religions and philosophies would wrestle with new evidence of continuity across time. Artists would find a new wellspring of metaphor, and politicians would race to frame narratives about ownership, interpretation, and access. Economies might pivot toward expedition funding and preservation science. Families would ask whether a message requires reply and who, if anyone, speaks for humanity. History shows that humankind can respond with awe, with reverence, and with reckless haste all at once. That is why protocols matter more than drama. The right path is methodical and global. Data must be open and archived with full provenance so independent groups can attempt decoding without selection bias. Confirmation should come from multiple observatories and from different wavelengths to rule out single-band artifacts. Blind analysis teams must test hypotheses without seeing anticipatory patterns and publish negative results as readily as positive ones. Any plan to approach the ring with probes or to retrieve material must be preceded by an ethic and legal framework negotiated internationally, with input from scientists, ethicists, indigenous voices, and the public. A temporary moratorium on dramatic announcements until peer review and independent replication would guard against premature panic and against the monetization of discovery. Visual storytelling can help the world grasp the mystery without fueling myths. Overlay animations that place decoded sequences over a rotating ring let viewers see how pattern and position relate. Interviews with signal analysts walking through their blind tests and statistical thresholds bring the method to life. Staged reconstructions that imagine possible senders show scale and intent without claiming fact. All of that work buys time and clarity because true authentication is slow. Probing fine dust at interstellar distances, building instruments that measure subtle polarization across a ring, and launching a close pass probe with sterile containment all take time measured in years and in decades. During that time, narratives will form and pressure will build to declare discovery early. Premature conclusions could become self-fulfilling or dangerously misleading. What if a cultural rush rewrites the tests or a political actor claims custody before replication? The human impulse is to leap toward meaning, but a whisper from the memory star asks for patience and for a chorus of careful listeners. Will we wait and let rigorous proof arrive, or will haste convert a tentative echo into a proclamation that the future may regret? A living ribbon of dust can join two planets like a sky highway. In the Skybridge worlds pair, a steady corridor of particles threads the gap between two neighbors, locked into place by gravity and by the whisper of magnetic fields. The deepest trick is simple and elegant. A pair of Lagrange balance zones and a matching orbital resonance carve a safe path where material can linger instead of plunging inward or escaping outward. Dust from rings and from small moons drifts into that corridor and then charges under stellar light and plasma, so the planetary magnetic fields cradle it like a riverbed holds water. The magnetic lines guide the grains, electrostatic forces keep them from dispersing, and gentle replenishment from nearby sources maintains the ribbon over centuries rather than hours. Stability demands patience and matching. The planets must share similar orbital phases and tilt enough to keep the corridor from shearing, and the stream needs a steady feed of new material to make up for losses to radiation pressure and a pointing Roberton-like drag which slowly pulls particles sunward. Shepherd moons or periodic cometary trickles can do that work, while controlled magnetic tethers and subtle fields shaping by orbital stations can nudge the bridge back into a calm geometry after storms. When the balance holds, the Skybridge becomes practical as well as beautiful. Commuter shuttles ride the bridge like trams on a line. They deploy magnetic sails and charged collectors that catch the slow flow of plasma and of dust, trading tiny impulses against the stream to conserve onboard fuel. Passenger shells tether between sparse anchoring nodes that keep G-loads low, and cargo rigs piggyback along steady lanes where particle density is high enough to brace a cargo tether but low enough to avoid abrasive wear. Daily life around a bridge gains its own rhythm. Morning commutes feel like a slow elevator between horizons, with cafes at each endpoint hosting early travelers and markets that open to trade fresh harvests and exotic orbital goods. Midday sees freight convoys that glide like long trains, and evenings bring cultural crossings where musicians and storytellers set up temporary stages on maintenance platforms, and the bridge itself becomes a moving promenade. Endpoints are magnets for markets because anything that can ride the bridge gets cheaper to move. Entrepreneurs cluster warehouses and transfer plazas in those port zones, while floating inns and capsule restaurants sell the novelty of a short transit across star-lit space. The cheap flow of raw materials spawns specialized industries. Microfabricators on One World export precision components as loose assemblies into the stream, and then other settlements pick them up and finish them with local labor. Artists ship light, sensitive pigments and glass panes as fragile cargo because the bridge reduces the shock of re-entry and buffering. The economy scales into surprises too. Real estate near a well-tended anchor point becomes prime, and a single firm that controls a particularly stable node can extract tolls and shape entire trade routes. That is where politics and law become unavoidable. Who owns a corridor that runs through shared gravitational space? Are bridges a commons to be stewarded by international agreement, or are they private highways that reward the builders who maintain their clamps and coils? Historical analogies are immediate and uncomfortable. Early canal builders on Earth gained power by bottlenecking transit and setting tariffs, and the same incentives play out when a firm controls a magnetic snare that gates a key anchor. Legal disputes erupt over transit rights and over environmental protection. Some nations insist on open access because the bridge supports entire planetary food chains and low-cost energy transfer, while private syndicates argue that without investment and active maintenance, the bridge will decay and the lost trade will cost everyone more. Enforcement is messy. Policing a skybridge requires patrol shuttles and neutral arbitration nodes in neutral orbits. Smugglers try to slip unregistered cargo through patchy gaps at the bridge's edge, and standardization of docking procedures becomes a diplomatic battleground. The hazards are physical and social alike. Microparticle abrasion slowly wears through hull skins and connectors, so shuttle engineering favors repair-friendly exteriors and sacrificial sheathing, and legal frameworks fund shared repair fleets as a public good. Magnetic storms can kink the stream and toss whole cargo lines into chaotic eddies, which is why early bridges included emergency safe harbors and automatic loopbacks that let vessels ride until the field calms. The built culture around a bridge is rich with rituals. Commuter etiquette becomes formalized. There are unspoken rules about how to carve space on a tether during rush hour, about who yields on the outer lanes and who yields on the inner. Bridge markets invent goods tailored to transit life snacks that will not scatter in microgusts, modular suites that fold into a commuter bunk for the long crossings, and musical instruments designed to play against the faint electric hum of charged dust. Festivals celebrate the replenishment days when a trailing moon ejects a new flourish of particles and the bridge blooms brighter for a season. Visuals turn this world into a moving postcard. An animated formation sequence shows particles funneling from rings into a narrow braided stream, magnetic lines visualized as glowing ribbons that corral dust into lanes. Commuter vignettes cut between a quiet shuttle docking at dawn and a bustling market where crates slide from orbital freighters onto conveyor arms. Time-lapses of trade in motion compress months into seconds so viewers can feel how a bridge reshapes supply chains and urban growth. Close-ups of tether splice crews at work, hands in protective gloves replacing a worn skin, and of children watching freight trains drift past under a low sky give the idea human scale. The final, irresistible thought is small and utterly delightful. Would you build a cafe on the bridge that traveled between worlds, a slow-moving table where strangers trade stories and spices as the stars slide by beneath your cup? The sky there is an endless bowl of saffron light. Thick aerosol mists hang low and warm, and when you walk into them, the world seems to glow from within. Those mists are not ordinary fog. They carry microscopic photonic crystals, tiny ordered structures whose spacing picks which wavelengths of sunlight get sent back to your eye. In plain language, a photonic crystal is a repeating pattern at the scale of light itself, a lattice of particles that reflects some colors and lets others pass. When billions of those crystals float together, they act like a living filter, turning the incoming spectrum into long golden afternoons or into sudden pockets of strange color where the light bends and plays tricks. The effect is both soft and sharp. Edges of cliffs can suddenly appear lined in molten gold. Distant hills can ghost into doubled horizons, and rippling fields take on depth as certain bands are enhanced and others fall away. At the right angle, you see halos and moire-like dances that move as you walk, and that make static landscapes feel animated. How do those crystals get into the air in the first place? The story is a mix of fire and breath. Volcanic aerosols are one source. Explosive eruptions loft molten silicate and mineral droplets into the upper atmosphere where they quench into glassy spheres. If conditions are right, those spheres can form regular surface textures or shell layers that act as photonic elements. Biogenic emissions provide a second path. Microbes and plankton can excrete silica-rich shells or complex organosilicate particles that self-assemble into ordered arrays. On some coasts and in shallow seas, blooms of engineered or natural microorganisms seed the sky with glittering detritus that climbs on the winds. Both geological and biological processes can work together. An ash cloud fertilizes microbial blooms. The microbes build shells from the new mineral flux, and then winds pick those shells into long-lived aerosol layers. Over seasons, the mist thickens into banded strata that wrap continents in saffron veils. The climate answers to that light as if the planet had a spare thermostat. Photonic crystals change not only color but also how energy is distributed. By selectively reflecting visible bands and passing infrared, the mists can cool the surface even while bathing it in warm hues, or they can trap heat by scattering thermal radiation back down. Local weather becomes a painter's mood. Valleys under dense bands of crystals may enjoy permanent amber twilight and slower diurnal swings. Regions where the mist thins in patches tumble into sudden brightness that feels like a sunrise replayed every hour. Rain chemistry shifts too. Crystals that nucleate water droplets make rain fall in faintly golden sheets, and ash-seeded clouds can carry rare minerals into soil in patterns that rewrite local fertility. The planet's ecosystems respond by tuning their pigments. Plants favor yellow-red bands that pass through the mist, so leaves and flowers evolve toward warmer palettes. Pollinators that detect contrast rather than sheer brightness thrive, and nocturnal species move their activity into the soft golden hours where predators and prey are traded in slow light. Human culture here learns to live inside the hue. Fashion becomes a study in tone modulation. Garments are woven from fibrous materials that shift reflectivity with simple mechanical folds, letting a sleeve flip from deep bronze to cooled amber as a person moves. Designers favor layered fabrics with tiny reflective lattices embedded so clothing can signal in a field of gold without needing bright dyes. Jewelry makes use of fractured photonic shards polished to sing with light, and weddings trade scented veils that catch and scatter saffron like a flock. Architecture adapts in ways that feel graceful and practical. Buildings wear double skins with photonic curtains that tune the incoming band mix. Interiors favor warm, neutral palettes and translucent partitions that hold golden light in gentle gradients, while plazas open to sky pockets where the mist thins and where direct starlight can be seen at night. Urban planning treats sun and mist as materials. Streets are angled to capture the most flattering mix for markets and theaters, and greenhouses use layered filters to bring back missing blue bands for certain crops while letting the ambient saffron forge a comfortable public light. Industry forms around the crystals themselves. Photonic materials are valuable because they perform filtering and guiding without power. Engineers harvest crystals for passive light modulators, for low-energy optical circuits, and for security inks that change hue with viewing angle. Extraction is careful work. Harvesters use electrostatic collectors, cold traps, and gentle sieving nets to pull microscopic crystals from the mist without shattering them. Some operations cultivate crystal farms by seeding microbial mats in sheltered bays, and then vapor lifting the formed spheres in controlled plumes. That creates an economy of cultivation as much as of mining, and it keeps the most delicate structures intact for use in high-precision photonic devices. Health is a steady concern. Fine crystalline aerosols can irritate lungs, provoke inflammation, and in some cases embed in tissues in ways that require long-term care. Photonic crystals that enhance particular bands can increase ultraviolet stress in unexpected pockets, making skin and eye protection routine for large parts of the day. Public health adapts with widespread filtration architecture, personal breathing masks that are as common as sunglasses, and timed exposure practices where schools and work cycles avoid the thinnest, most abrasive haze. Medicine also lends beauty to safety. Designers make filters and masks into statements that match clothing and civic identity, turning protective gear into cultural artifacts rather than mere burdens. Visually, this world is generous to cameras and eyes. Panoramic saffron dawns roll like golden oceans, and wide shots of terraced cities look as if someone painted the light into every balcony. Close-ups of photonic crystals under a microscope reveal their ordered lattices, and macro footage of a single drifting shard catching the sun will feel like watching a living jewel. Street life filmed at midday shows vendors under canopies that filter bands into sweet tones, and children racing through fountains where the spray catches gold like confetti feels intimate and human. The smallest scenes matter. A baker loads loaves into an oven under a saffron awning, and the crusts take a particular bronze glow that becomes locally prized. A cafe patron swirls tea in a cup and lifts it to a face framed by soft golden light, and every detail of color and texture is suddenly richer. What would breakfast taste like under saffron skies? A deliberate darkness can become the axis of a civilization. Around the obscured city star, a ring passes like a slow blade, carving scheduled nights into the days of whole continents. From a distance, the system looks like a halo of motion. Up close, the light falls in precise swaths, a choreography of shadow that repeats with such reliability that calendars and courtships both learn to count its beats. The effect is eerie and domestic at once. Streets that glow like rivers under starlight one hour can be wrapped in velvet dusk the next, and every window, every market becomes a timed aperture to a ritual of alternation. There are two plausible stories for how the ring came to be. The natural tale is patient and mechanical. A past collision or a swarm of shepherd moons leaves behind dense ringlets of ice, sulfur-rich dust, and metallic fragments. Gravity corrals this debris into narrow arcs and resonances. Over millennia, those arcs settle into lanes that skirt the star at just the right distance and inclination to sweep shadows across inner worlds on every rotation. Small moons keep the lanes thin and coherent. When a shepherd crosses the ring, its gravity corrals material and closes gaps, so the shadow returns like a well-polished cue. Observers chart the lane's precession and can predict exactly when a particular city will feel the dark. The artificial version tells a different story. A network of orbital habitats and engineered shades circles the star like a ring of silent sails. Maybe a civilization long ago built them to tame starlight for climate control, to block harmful bands, or to signal across interstellar emptiness. The structures might be habitats and power collectors, arranged in a deliberate lattice that doubles as a veil, or they might be purpose-built screens, adjustable in tilt and opacity, that create scheduled eclipses as social infrastructure. The signatures differ in subtle ways. Natural ringlets betray clumps, irregular grain size, and thermal emission across broad bands. Artificial arrays show geometric regularity, engineered materials with narrow emissivity, and coordinated motion patterns that optimize for a schedule rather than for orbital equilibrium. Either explanation is plausible when data is thin, and the debate is part science and part myth. Orbital mechanics is the language that turns mystery into timetable. A ring's shadow sweeps where the ring's orbital plane intersects the world's rotational equator, or where geometry aligns with a city's latitude. If the ring sits close to the star, the shadow can be broad and slow, spanning hours. If it orbits further out, the shadow narrows and the transit is sharp, like a blade across a skyline. Resonances between the ring material, any shepherd moons, and the planet's rotation lock the pattern. That locking explains why entire civilizations can plan decades ahead around predictable eclipse windows. Observers measure slight drifts and then build compensations into law. A change in the ring's inclination by the width of a finger can shift the shadow path by thousands of kilometers, so monitoring teams are as important as weather services. Society bends to the beat of scheduled darkness in ways at once clever and intimate. Architecture becomes a craft of anticipation. Buildings are dual facades that open like concert halls or seal like shells. In light, windows' whole floors expose glass and terraces that drink sunlight. When the shadow comes, a building's outer shell slides, panels rotate, and inner courts bloom with stored warmth and phosphorescent art. Planners design light wells and sun reservoirs that capture and store midday radiance in thermochemical batteries, releasing it through the eclipse to keep interiors gentle and alive. Streets are layered with retractable canopies and with reflective channels that concentrate the last rays into concentrated gardens. In low-tech districts, people grow their lives around courtyards that become stages when the city darkens. Entertainment economies flourish wherever darkness is scheduled. Night markets sell goods that make sense only in shadow, textiles that flourish under a low blue spectrum, and culinary stalls that rely on the cool hour to flame smoked dishes without overheating. Theaters schedule premiere performances during the deepest eclipses, and choreographers compose dances that only resolve when orbital gaps let starlight cut through in a slit. Artists choreograph shadow plays that ride the ring's motion, timing dancers to step into slits of light like actors in a moving cathedral. Musicians tune instruments to the hush of eclipse hours, and streaming networks sell synchronized darkness experiences to millions who tune in from other cities to watch a particular urban plaza fall into its scheduled night. Work rhythms change in practical ways. Agricultural cycles split into two economies. Light-bound crops grow under the open hours, and fast-sprouting varieties are cultivated to sprint through brief luminous windows, while slower crops nestle in insulated greenhouses that sip stored energy. Industrial processes that require constant temperature run in heavily shielded chambers. Night shift is not a social stigma here. It is often the prime moment for gatherings, for performance, and for quiet creativity. Municipal services employ eclipse coordinators, those who manage the transition of light and who run safety sweeps to check that moving panels and public canopies operate without jamming. Transit timetables fold around the shadow-s sweep because a bridge that crosses a city at the wrong point can be plunged into near darkness for the duration of a transit window. Psychology turns in on itself in this alternating world. For many, the schedule is comforting. Predictable darkness feels like a communal heartbeat. People mark their time to it, and rituals build around its regularity. Children grow up learning the eclipse calendar the same way other children learn seasons. Creativity often sharpens under constraint. When light is limited, artists compress ideas into small luminous moments. A poet writes stanzas that must resolve within a single eclipse, and architects design a room that tells its story only when the shadow arrives. The forced focus prunes distraction and intensifies attention. Yet there is another face. For some, the enforced dusk is a slow melancholy. Human circadian systems evolved under a broad cycle of light and dark, not underneath a daily cosmic curtain. Even predictable darkness can erode mood when sunlight is a rationed commodity. Populations in peripheral regions that only rarely see the star's unfiltered face report higher rates of seasonal languor and of longing for permanent day. Societies respond with light therapy clinics, with public brightness lounges where trained technicians recreate a full spectrum, and with social rituals designed to remember the star's full glare. The politics are subtle and sharp. Control of ring adjustments or of mirror arrays that can spoil an eclipse for a fee becomes a lever of influence. Debates over whether to deploy emergency brighteners to rescue crops during a misaligned shadow or to preserve the integrity of an ancient schedule echo old arguments about technology and tradition. Religious groups may sanctify the dark windows, forbidding their violation, while merchants lobby to expand artificial day to increase shopping hours. The ethical stakes feel immediate because the ring is both environment and culture. For creators, the image is irresistible. Visuals could show choreographed shadow cycles sweeping across glass and stone, plazas that change mood like theater sets, and cross-sections that reveal strands of ringlets and shepherd moons locking into resonant choreography. Interviews with residents bring the human poems into focus. An elderly baker could describe waking at the first slit of light to bake loaves that must finish before eclipse, and a young choreographer could speak of composing a piece that only resolves in the 3-minute gap between two shadow bands. Close-ups of adaptive facades sliding into place and of children tracing eclipse marks in the dust make the phenomenon feel lived and precious. In the end, the obscured city star asks a quiet question. Does living with scheduled darkness sharpen creative constraints into dazzling new arts? Or does it lay a slow melancholy across a population that misses an unbroken sky? Which side of that balance would you choose if your nights were always on a clock and your days came with an appointed end? Some star systems have holes where whole worlds should be. Astronomers point their maps at a dusty disk and find a stretch that carries far less mass than models predict, and then, nearby, a handful of compact, brilliant blue objects that seem to hold that missing weight in tiny packages. The mass distribution maps are the first clue. When you chart how matter spreads across a disk, you expect smooth gradients sprinkled with clumps where planets grow. In a sapphire void, the chart looks lopsided. Radial slices show deficits the size of entire moons, and yet the gravimetric signals from the region hint at concentrated mass in objects no larger than small planets. Spectra add another layer. Ordinary dust and gas have familiar fingerprints across visible and infrared light. The sapphire-like objects throw unusual scattering patterns and narrow reflective bands in the blue and near blue-green part of the spectrum, so they appear literally gem-like when rendered in color maps. Put the maps and spectra together and you get a riddle. Where did the mass go, and why does it sit in a handful of intensely compact, blue-gleaming bodies rather than in a population of planets and belts as expected? Scientists offer several hypotheses, and they range from cautious to radical. The conservative story borrows from known processes. Turbulent clumping and fast pebble accretion can, under the right disk conditions, funnel a large fraction of solids into runaway agglomeration. Instead of many protoplanets, you get a few hyperdense cores that squeeze material under shock and heat into crystalline phases that refract and scatter light like sapphire. Those phases might be corundum-rich layers or dense aluminum and oxygen compounds that form under extreme localized pressure. Another natural route uses electromagnetic shepherding. Charged dust in a magnetized disk can lock into filamentary streams and then collapse into tight knots where collisions and annealing produce glassy, gem-like crusts. Those mechanical stories keep the system within the universe we know but nudge toward rarer outcomes. The more speculative explanations are bolder. If pressures inside an accretion shock are extreme and prolonged, you could form diamondoid or corundum cores of unusual density that are far smaller than a planet yet concentrate a lot of mass. Even wilder is the idea that a pocket of exotic condensed matter condensed into a stable, ultra-dense phase that behaves unlike normal rock. Those ideas sit on the edge of current physics and demand more than a beautiful image to survive. The consequences of either path would rewrite parts of planet formation theory. Standard models assume mass spreads into many embryos with a balance between collision growth and orbital scattering. A sapphire void shows that under certain conditions that balance tips toward concentrating solids into compact gems and leaves the rest of the disk unexpectedly bare. That forces rethinking of how turbulence, magnetism, and shock heating sculpt outcomes, and it raises the possibility that planetary architectures are not universal but highly conditioned by ephemeral disk states. For future resource hunters, the lure is obvious and complicated. A shard of sapphire-scale material with extraordinary density is a different kind of ore. Its optical purity could make it a perfect substrate for high-performance optics and photonics. Its strength-to-mass ratio might enable lighter yet tougher habitat skins and structural beams. If metallic or doped with exotic elements, these objects could also be a rich source of concentrated metals and rare isotopes. The catch is simple. Concentrated mass means concentrated difficulty. Mining such bodies demands tools that can chip through crystalline lattice without shattering desired optical structure. Operations must deal with extreme local gravity wells if the objects are denser than expected, and they must manage the dynamical consequences of removing mass from a finely balanced system. Small missteps could fling fragments into the rest of the disk or collapse delicate magnetic structures that keep the void stable. Imagery sells these stakes. Show mass distribution maps that light up empty lanes beside glowing blue nodes, and then pull into close cross-sections of a sapphire object where lattice planes refract a star-esque light like a cathedral window. Cut to speculative mining platforms anchored with magnetic clamps and to microtunnels lit by blue shards that glint when a core sample draws out a filament of exotic crystal. Show chained processing barges that polish thin faces into lenses and that pull down strings of dust to feed a local economy. Those scenes tease both wonder and engineering friction. Through all the wonder, the scientific rules of evidence matter most. Extraordinary claims demand extraordinary verification. What instruments would turn a tantalizing map into a confirmed discovery? High-resolution, long baseline interferometry is essential because it resolves structure at the scale where a compact mass could hide in a disk. Submillimeter arrays and space-based infrared observatories can measure the thermal signature of those nodes and reveal whether they are cold, hot, porous, or solid. Precision astrometry and transit timing analysis track the tiny gravitational tugs these objects exert on nearby matter and can measure mass independent of brightness. Polarized spectroscopy across visible and near-infrared bands reveals whether scattering arises from ordered crystal faces or from ordinary particulate grit. Radio and radar sounding can probe subsurface density if we can send probes into the gap, and careful Doppler tracking of a close flyby craft would map the gravity field like a surgeon mapping a pulse. Finally, nothing replaces in situ sampling. A sterile probe that brushes a surface and returns raw mineralogy to a clean lab will collapse 1,000 debates into a single rich data set. Those missions are hard and costly, and they require international cooperation and patience. Until then, the sapphire void sits on the list of the most tantalizing anomalies in the sky, a place where mass seems to have been rewritten into gemstone giants and where future engines of industry and curiosity might one day learn to cut a planet into a story. What instruments would you build first to prove whether the sapphire glow is natural sculpture or a sign of something far stranger? Some lights refuse to die. Out beyond the ordinary maps, a faint halo circles a dark, dead star. Tiny suns float there like embers pushed into orbit. Each microsun glows with a small, stubborn furnace, a lick of fusion or residual heat that refuses to yield to the cold around it. From a distance, the halo looks like a string of salt lamps strung across a black ocean, and up close, every one of those lamps holds a world of possibility and loss. There are a few ways those microsuns might come to be. One idea begins with violent disassembly, when a massive star fragments in a catastrophic event and leaves compact lumps of hot plasma and fused material scattered in orbit. Those fragments cool and shrink but can retain enough internal pressure to glow for ages as miniature furnaces. Another path involves captured embers from brown dwarfs. A dying substellar object that once smoldered on its own can be nudged into a trapped path around a larger remnant and slowly leak heat into the surrounding space for long centuries. A third, more unsettling option is deliberate engineering. An advanced civilization might harvest the last of a star as fuel and cast it into many contained microreactors, spreading warmth across a neighborhood to preserve life and memory when the central star can no longer support whole worlds. Whatever their origin, the physics that makes habitability possible around these specks is intimate and local. Heat from a microsun falls off quickly, so habitability is a fringe art. Tiny zones of warm atmosphere hug the light source where gravity or engineered containment can hold gases against escape. Reflective rings and light sculptors concentrate and redirect photons so a distant terrace can feel like a morning for a short span of rotation. Thermal pipes and radiative chimneys move warmth from the furnace into greenhouses and communal halls. Magnetic fields and tethered plasmas can help trap charged particles and form thin magnetospheres, which reduce sputtering and preserve whatever air a community manages to keep. In short, life on the last light is a careful balancing act between proximity and protection, between the need to be warm and the need not to be consumed by the flame. The human stories around these oases have a particular kind of poignancy. Some settlements cling to a single microsun like a family tending a hearth. Houses radiate outward from the light, terraces arranged to catch every usable band of radiation. Children learn to read the star by heat rather than by color. Some communities are nomadic, small fleets of barges and tethered platforms that drift from light to light, harvesting what they can and leaving memorial stones where a microsun has finally dimmed. Others are archivists. They preserve the smallest of embers as ritual relics and as libraries of a stellar past. They weave stories around the pattern of the halo, set chants to the cadence of each dimming, and keep oral records of the sweet warmth that once defined an age. And then there are those who break with preservation for survival. Engineers, traders, and desperate governors debate whether to siphon a microsun to feed a larger hub. The logic is cold counting of energy and mass. A single furnace tapped carefully can power a city-sized habitat for generations. Multiple small lights cannibalized together could create a more stable, longer-lived heart. But every act of harvesting is also an act of erasure. Pulling apart one of the last lamps takes a story with it. It ends a living archive, and it shifts the halo toward fewer, brighter sparks at the cost of diversity. Those choices shape law and custom. Some polities criminalize any harvest without community consent. Others auction microsun cores to the highest bidder. Black markets develop for smuggled microreactors and for the mechanical heart pieces that tune output. Ethical councils form in dim halls to argue whether a flame can be owned, whether a remnant that burns can be considered property, and whether the duty to preserve outweighs the duty to keep people alive. Visuals for a creator could be devastating and beautiful at once. Panoramic shots should show the halo pinned against utter dark, each tiny sun a distant flare, and the camera moving between them like a slow pilgrimage. Intimate portraits work best in the warm glow of a hearthlight that is literally a star, where an elder folds brittle maps beside a window and a child cups a palm toward a filament of heat to learn the difference between living and memory. Archival-style sequences could weave grainy footage of former full stars, song recordings of festivals that honored the bright era, and slow voiceovers that read names of lights that have gone out. Technical scenes can show long tethers and arrays of mirrors that steal photons from a flicker and hand them to a greenhouse, and cutaways can reveal the engineering trade-offs when a community decides to siphon or to stitch. The moral math is messy and human. Let a microsun burn until it dies natural and risk slow disappearance across the halo. Harvest now and give life to many while erasing particular loci of history. Create engineered microreactors and spread warmth deliberately, but at the cost of replicating human agency in the place of a natural end. The dilemma is a kind of tragedy that repeats itself across scales. It reads like a question of caretaking and of courage. Is saving the last lights an act of stewardship and fidelity to the cosmos? Or is it the beginning of a different kind of decline in which every last ember is used up to prop up a widening human footprint? Who decides which light lives and which one is given up to fuel a future? If you stood on a terrace lit by a single tiny sun and heard the halo hum like a distant cathedral, would you push to kindle another ember from its neighbor? Or would you sit and hold vigil while the light runs out on its own time? We have traveled through 35 astonishing star systems. Some were optical wonders that split and painted light into living galleries of color and glass. Others were gravitational oddities that bent space and time and traded moments like a scarce currency. We saw bioengineered belts and luminous gardens that turned dust and ice into tools for life and signals for navigation. We confronted speculative techno-signatures and sleeping relics that ask us how to read evidence and how to act when discovery feels like a responsibility. Throughout the journey, we kept a steady balance between careful science and imaginative speculation, testing what instruments can verify while leaving room for the stories that push questions forward. Which system sparked your imagination most, and how would you live, work, or create culture there? Share your top 3 picks in the comments and tell us which world you would choose to call home. If this voyage fed your curiosity, please like the video and subscribe for more deep space explorations. Up next is a practical toolkit video on the top 10 technologies you would need to move to a ring world and how those devices would shape daily life. An end card could show a montage of all 35 systems fading into a single star field, so each wonder melts into the next and the choices we make drift with them. Until next time, clear